Okay, good morning, everyone, and welcome back, everyone here and online. Say hi to the camera. We have a great morning of presentations for you. I think we've got field geophysics and then followed by a session on the lithosphere. If anybody has any questions about anything or if you need any help, we're having lunch. We'll have boxed lunches after the session. You're all welcome to stay around for as long as you like. If you need help getting Ubers or anything like that, Michelle said to make sure you let her know. This morning's session is going to be chaired, the first session, by Tara Shreve. Tara's a postdoc here working with Diana and Laura. And Tara, I think you can take it away.
Thanks, Mike. Thanks everyone for coming today for the Field Geophysics session. We're going to have 4 speakers today talking about a variety of topics from deep mantle dynamics to volcanoseismology. Our first speaker is going to be David James, who's going to be speaking about broadband portable array seismology and multidisciplinary science, lessons from the CapVol project. David?
No. I'm on? Okay. Let's go back one. Yeah, it's a pleasure to be here and participating in this tribute to Rick, who has become very obvious to many by now, has been really a driving force in this department for many, many years. But as many know also, I've been out of active science for the last almost decade. And so I've taken as my assignment to touch on the period around the time of Rick's arrival at DTM and the very pivotal years that followed. Anyway, there was a period in the late 70s, in the mid 70s, where DTM geophysics was very much in a sort of a holding pattern. In 1977, I think Fuad Terra came on as a staff member. In 1980, Rick, and shortly and a few years after that, Steve. And they made up the nucleus of a group that simply it wasn't just an evolution in geochemistry, it was a revolution in geochemistry. And it just made an astonishing leap in the capabilities and range of analytical facilities at DTM, and consequently a huge expansion in the scope and the depth of the science that was being done. What may be less well known at this time, at least to this audience, was that it was also a revolutionary period in the 1980s in field seismology. And as an aside, I should say that that the imposter who had been masquerading as a geochemist, as a result of this revolution in geophysics, was able to make a quiet exit back into geophysics. And at any rate, in that period of parallel advances in geochemistry and geophysics, Rick was the one more than anyone else who saw most clearly the potential for coordinated multidisciplinary studies. And specifically, he recognized that dense seismic arrays that were capable of imaging deep structures could be critically important to tackling problems ranging from craton formation in the Archean to modern volcanism and intraplate settings. These just happen to be Rick's interests. And one of the things I should say is that besides his other talents, he has an amazing talent at convincing people like seismologists that what he is studying is the most important problem in geology at the time. At any rate, I'm going to talk about the first of these Rick-driven exercises, which became the CapVol project. And that explains my choice of the first slide here. You'll see the iconic mantle nodule sitting there, behind which is lurking Steve on the left, Rick in the middle, and very importantly, Joe Boyd on the right. And Joe hasn't come up very much in these meetings so far, but he was absolutely critical in carrying out the experimental petrology and the mineral physics. They gave us the tools gave us the tools from which he was able to develop geobarometric, geothermal barometric systems that gave us, from which we could calculate, for example, what was the depth, what was the pressure and temperature from which that nodule came. Let's see here. Okay, so I'm going to talk first about the crisis in portable seismology, which came coincidentally almost exactly at the time of Rick's arrival here. The first one is, even as late as the 1980s, portable seismology and the study of continental structure was confined largely to crustal studies using explosions with a whole hodgepodge of homemade recorders. There were no data standards whatsoever. Really, it was a period of time when our ability to study the crust, and particularly no ability at all to really study the deeper lithosphere. So in 1980, the National Academy of Sciences, with NSF support, impaneled a committee to study a major new initiative. They called it Seismic Studies of the Continental Lithosphere, the so-called SSCL report. And it was issued in 1983. It recommended that substantial numbers, 1,000 or more, of new generation digital seismographs be acquired for 3D high-resolution imaging of continental lithosphere. This was following on the heels of that report. The program for array seismic studies of the continental lithosphere, Pascal, emerged in a little over a year. Pascal was part of IRIS, which was Incorporated Research Institutions for Seismology. It's also formed up at the same time. I call it how seismologists finally got their act together. The challenges of imaging the Earth at geologically meaningful plate tectonic scales really demanded radically new technologies, vast increases in the numbers of high-performance seismic instruments, and vast increases in funding. Okay, so the IRIS Consortium was formed to promote the development and large-scale acquisition of advanced instrumentation. They first was Pascal to acquire several hundred transportable broadband seismographs and their auxiliary gear in support of large-scale PI-driven array studies. And I should mention that as part of Carnegie's involvement in this, the institution sprang for 25 of these broadband instruments for the department itself, almost $1 million. And that was really came in parallel to the formation of Pascal, and Pascal acquisition of instruments. The Global Seismic Network I mentioned because at the time the Department of Defense was supporting something called Worldwide Standard Station Network, WWSSN. It was being phased out, and seismologists were faced with the prospect of having hardly any certainly a much depleted stock of instruments globally. So the Global Seismic Network was part of IRIS to deploy and maintain state-of-the-art digital global stations. And not mentioned often enough is the Data Management Center to archive digital seismic data and make it rapidly available worldwide through the internet. In the 1980s, this was really a radical idea. Right now, I think the Data Management Center probably has several petabytes of data, all of it online and accessible. I showed this picture is of a Streckeisen STS-2, and it was developed in Switzerland by a guy named Streckeisen, and it is a low-power, 3-component broadband seismometer. It is the first of its kind, and it was by virtue of this breakthrough in these capabilities had never been possible before. It could record high-frequency P waves, could record lower-frequency S waves, and all the way into the surface wave bandwidth. And it was portable, and as I say, low power, and 3-component. So I mentioned that because this was critical to the advent of portable broadband arrays. The broadband STS-2 sensor, coupled with low-power microprocessor-based digitizing recorders, and compact mass storage devices made possible 3-component transportable seismograph systems. I should mention that the microprocessor-based digitizing recorders also were just becoming available in the late part of the 1980s. But these recorders could record earthquake waves across the broadband seismic frequency spectrum all the way from P waves into surface waves. They could record digital data continuously and autonomously, unattended, with standalone power for months at a time. So these were semi-permanent installations that were put in to record earthquake waves around the world that would be used, the arrivals for which would be used subsequently for imaging. And most important and not very often recognized is we were able finally, because of GPS, which coincidentally came in about the same period, we were able to lock in accurate absolute timing. And this was a very key element because for a closely spaced array, we're looking at very, very tiny time differences between stations. And unless we have an absolute time lock system for every station, we're really looking at awful lot of noise. And of course, it gave us better station locations, but the key thing was the absolute timing. I just mentioned very briefly scales and resolution. The global imaging with typical scale lengths of 1,000 kilometers, low resolution, but big picture, we see lots of those. And then the portable array imaging at variable scale lengths. It was typically 10 to 100 kilometers, but they could be set up to measure at almost any scale that you wanted. And the important thing was that you could achieve resolution at geologically useful scales over targeted regions of study. So let's get to formation and evolution of cratons, lessons from Southern Africa. We mentioned just the principal collaborators. Rick was very much a driving force behind this. I was involved in this. Steve was involved, Matt Fouch, a number of our postdocs. I wanted to particularly point out Teresa Gure and Jane Gore, two African women who got their PhDs as part of this study. And another, Arthur Snoke, was a postdoc. And then, of course, our high-flying MIT colleagues, Tom Jordan, Tim Grove, and others, and what we call the Kapval Seismic Group. And finally, the Southern Africa collaborators, the University of Cape Town, Witwatersrand, Zimbabwe, and so on. Altogether, 28 institutions were involved in the Kapval project. So this is an anatomy of an Archean craton, the Kapval. Why Southern Africa? Okay, first of all, it should be, which is obvious to this group, that of course that the Kapval contains nearly 1 billion years of Archean history. It is, in many senses, the cratonic type locality in the world. The region is perforated by all kinds of kimberlite pipes that have delivered a mantle and deep crustal samples to the surface. It's ideally suited logistically for seismic studies. And I should mention, coincidentally and serendipitously, 1995, which is when we started to put together this project, was the same year that South Africa came out from apartheid. And up until that time, I don't know how many, or probably so many are too young to remember, but basically South Africa was constrained from participating in global science. And by the same token, scientists were constrained about working in South Africa. So in a way, in a very, very real sense, the Kapval project was a real scientific coming out for South Africa. And that was one of the things that made it, that the enthusiasm with which the South Africans and the companies in South Africa greeted the project was quite remarkable. So the questions were, how do 3D seismic images of mantle heterogeneity and crustal thickness relate to the assembly history of the craton? Why is the Archean different? What accounts for the longevity of its mantle roots? What does that mean in terms of, now remember, I'm talking about all of this back in 1980s, in terms of lithospheric formation, and is cratonization separate from crustal formation, and over what time interval did craton stabilization occur? Okay, topics for discussion. I'm going to talk very briefly about key results from geochemistry and mineral physics, rhenium, osmium. I promise there's not a single mention anywhere in here about neodymium isotopes. So you can rest. Yeah, you can sit back. We're going to talk about crustal age versus mantle age, temperature depth profiles of the mantle. That again from the geothermal barometry, Joe Boyd's work and others. Then we're going to go into talk about seismic imaging, the nature and composition of the Archean crust and mantle, PNS wave tomographic images of the upper mantle, predicted seismic velocities from the analysis of Kapval xenoliths. This was quite important that we were able to actually compare xenolith velocities with observed velocities. And finally, talk about something about crustal thickness and composition, the nature of the moho, and lower crustal flow in the Archean, and some conclusions and conundrums. Okay, I don't really need to labor this at all, but rhenium-osmium isotope studies were just coming on. Steve Shirey and Rich Walker, I think, were instrumental in that. The key points are that during melting of the mantle, which is what we're looking at in the Archean, rhenium is moderately incompatible, so it goes into the melt. Osmium is strongly compatible, so it stays behind in the residue. And therefore, melts will have very high rhenium-osmium ratios, and the mantle residues will have very low rhenium-osmium. So the osmium isotopic ratio should be similar to that at the time of depletion. So this is, in other words, the rhenium depletion model age. And very importantly, mantle osmium contents are high compared to infiltrating melts, so that it tends to be pretty insensitive to metasomatism. Okay, so if we look at results from rhenium-osmium model depletion ages for the principal kimberlite localities in southern Africa, the blue is greater than 2.5 GA, green, mostly the area of the bush belt, and reds are the less than 2 GA. So we go from the Cape Fold belt up through the Namakwa Natal belt, through the older fold belt areas into the Kapval Craton itself, with rhenium-osmium model ages greater than 2.5 billion years, up into the bush belt, which is a 2 billion year, 2.05 disturbance. Then the Limpopo belt, which is a collisional belt between the Kapval Craton and the Zimbabwe Craton. All of these cratonic ones are showing rhenium-osmium model ages greater than 2.5 billion years. So the conclusions from the geochemistry is, first of all, is that the cratonic keel is Archean in age. There's no surprise there. But it is also not age stratified with depth, as far as we can tell. Eclogites are the same age as the depleted peridotites. Is that true, Steve? Okay. Is that still true, I should say, Steve? Laboratory studies and results from eclogite xenoliths suggest that the subduction processes were important in the Archean. And clearly, cratonization was not a discrete event, but occurred in stages, and final mantle stabilization may post-date crustal formation. I added a postscript here that for the fascinating parallel story behind the diamond inclusions, which I have not included in this talk, you should chat up Steve Shirey, who will provide full details. Seismology. Okay, we finally get to the seismology. The upper mantle structure from tomographic analysis, and the crustal structure from receiver function analysis. Here's the Southern Africa seismic experiment. It's at that time by far the largest portable array experiment ever undertaken. This shows the stations. There are 54 broadband stations. That was what was available to us at the time. That included the 25 Carnegie stations. They were deployed at 82 sites, and these remain in place. These are really semi-permanent installations. They remain in place for 2 years typically. And so there was a 2-year deployment, and then they were moved to new localities, and another 2-year deployment. The grid spacing was typically 100 kilometers, and the widest dimension of the array comes all the way from Cape Town up here into Zimbabwe is about 1,800 kilometers and about 600 kilometers in width. I want to point out here a little telemetered array, which turned out to be very important, of broadband stations deployed for 6 months around Kimberley in a little 70 by 40 kilometer plot here right in this little area here. This shows a Huddle test. These are the STS-2s. This is Adriana Cunell, husband Randy at the time. And these were the recording instruments, all of which have been, of course, replaced with more modern instruments. But this just shows getting ready to head into the field. Field work in Africa. Southern Africa, first of all, was really ideal logistically for seismic studies. This shows a couple of pictures. This is Suzanne Vanderlei. This is Jane Gorey, who was one of the African women who got her PhD. She's shown here fiddling around with an STS-2 down the vault. So the STS-2 sits in the bottom of this. This is what's called the doghouse. On top are 2 solar panels, and actually at some point will be put a GPS receiver on the top here, but it contains the battery and the recording equipment inside. And so these broadband stations are actually little mini observatories. As I say, they remain in place for at least a year to 2 years. The tomographic imaging, what are we talking about? We're looking at relative delay times determined by cross-correlation of all waveforms. Typical standard deviations are 0.03 seconds for P, 0.06 seconds for S. The P wave, the S wave data are inverted independently. All the data are corrected for elevation and crustal delay times. And the inversion includes 3D velocity perturbation field. In other words, what we actually get out of it is not absolute velocities, but velocity perturbations off of a mean. But it includes earthquake location and station corrections, which means that the velocity model is constrained to contain the least amount of structure that is required to satisfy the data. So earthquakes for tomography, we use earthquake waves. What we want ideally, here's the array, Southern Africa Kapval array here. These are the earthquakes we use for the P wave phases. And what we're looking for is a good azimuthal distribution of waves, of sources. And here are the events for the S waves. Why do we want a good azimuthal distribution? This I go through very quickly here, but imagine that this is the surface of the Earth up here, and each of these little points here are stations. These different colored rays are earthquake waves from different events around the world coming into these stations. What we are looking for is a lot of crisscrossing rays right in this area. This is the methodology of a CAT scan. And the tighter we can get, the more crossing rays we can get, the better we can produce the velocity structures underneath. But we're looking for seismic velocity structures in this area of crossing rays underneath underneath the array. Okay, this is actually one of the early results, but this is a cross section at depth 150 kilometers. This again is the array. We're looking, this cross section here, we're looking at B prime, the central area. So we're going all the way from the Cape Fold belt up through the Namakwa Natal belt, into the Craton, across the Bushveld area, back into Limpopo collisional belt, and back up into the Zimbabwe Craton. We start to lose resolution up in this area here. And this is the cross section here. And what we can see very clearly is that these high velocities, the blues are high velocities, the reds are low velocity, should have mentioned that earlier, that they really extend down at least to 250 kilometers, and probably somewhat more. There's not much evidence of them extending much below the area of, this is probably, a lot of this is smearing downward, but there's probably very little below about 300 kilometers depth. So the conclusions from tomography is that the upper mantle images exhibit clear correspondence with the geologic terrain boundaries, and the contrasts tend to be vertical or nearly vertical. The cratonic root structures are irregular, with high velocities extending to at least 250 kilometers in the southern part of the Craton. The mantle beneath the 2.05 GA Bushveld province and its westward extension exhibit anomalously low P-wave velocities. It's clearly a disturbance in the Proterozoic. And then the mantle beneath the Archean Limpopo mobile belt has a dominantly cratonic signature. Okay, this is now work that is based on a lot of the work of Joe Boyd. We were calculating P and S wave velocities on the basis of equilibrium pressure and temperature at the mantle source. So we're looking at everything from the spinel larzolites, which I've just grouped here at 50 kilometer depth. This is P wave velocity here, depth here. This is S wave velocity in the lower one here. Ignore these Prem and Iaspe are just standard Earth models. You could ignore those for the purpose of this talk. But what we see is that if we took PM is the predicted velocity, seismic velocity, if we started with a primitive mantle material. And that would be under the conditions of a cratonic geotherm. That is obviously the velocities, the P-wave velocities are much lower than they are in samples that we actually see, which are spinel larzolite, back up into the low temperature garnet larzolites and Harzbergites, and then these are the fertile sheared nodules here. But basically our curve comes up like this, well above what we would expect for even a low temperature root with primitive compositions. The S wave is the same. It declines with depth because the temperature is a more critical component than the pressure. But again, the same thing. They're higher velocities than we would get if we were looking at primitive mantle. So I'm going to go on to crustal structure, how cratonic crust differs from continental crust everywhere else. I'm going to talk about receiver functions, and I'm not going to labor this, but basically a receiver function is this. Imagine that this is the MOHO here, that this is the surface of the Earth, and here's our recording station. Suppose we got a P wave coming in here, and it converts to an S wave, and it comes up to the surface. And we take the horizontal components and we rotate them to radial and transverse. So we look at the radial component, which will have the S wave signal. So we're looking for converted phases from the P wave to an S wave. And there are various crustal reverberations that can be included. The nomenclature is 0P, 1S means that we have one leg of S wave and no legs of P wave in this particular one. If we look at 1P, 2S, comes up as a P wave, goes to the surface as a P wave, converts to an S wave, bounces down, bounces back up to the surface also as an S wave. So that's 2 S's and 1 P. And similarly, 2P and 1S, we can come up and have a P wave and then bounce down as an S wave and then back up as a P wave. This is represented, this is the direct arrival here once we so-called deconvolve the records. This is the P wave arrival here. Now this is just a theoretical, what we should get. So this is the direct P to S conversion. This is the 3 Ps where we get a bounce, bounce, bounce all in P wave. Then we have 2P, 1S, so it's this one right here. It comes up, comes up as a P wave, goes down as an S wave, converts back to a P wave. And then so-called 1P, 2S, which goes up as a P wave and bounces down as an S wave and back up as an S wave. So this is what we should see in practice. In practice, we very, very rarely see anything other than this signal right here. And in fact, so this is the receiver functions for the MOHO depth image is arranged by geologic province. Here's the cratonic signals. This is now the P to S conversion that we're just looking at. You can see there's very little that shows up subsequent to that. And, but you'll notice that these are in the cratons, these are very prominent images. These P to S conversions are very clear. And when we get into non-cratonic, if we look at the marginal zones, which are basically still cratonic, we see that we get good signals from the Limpopo, from the southern marginal zone. But in the central zone, the collisional belt is just a mess. Bushveld province, similarly a mess. Okwa, Case Belts, Namaqua and Atoll, none of these show up anything like what we get in the cratonic areas. So this is telling us that the MOHO in these cratonic areas is much sharper. The velocity contrast across it is greater, and it's a much cleaner conversion that takes place. So we can from the P to S conversions, we can calculate crustal thickness, and you'll see we start out with very thin. Crustal thickness very thin down in the coastal belt, thicker up here in the Namaqua and Atoll mobile belts. The thinnest crust tends to be in the craton, thicker up here in the Limpopo belt and the Bushveld, and then thin crust back up into the Zimbabwe craton. And this is very characteristic of the cratonic crust, that they are in fact thinner and they've got a better MOHO contrast than the areas outside the craton. This is the capfall. This is the kimberlite array here, the telemetered array. These show some of the permanent stations, but we're going to look at receiver functions just at this group of telemetered array, and they're all where we can. So we're going to look at where the seismic data from the provides 3 independent lines of evidence for a very sharp MOHO beneath the undisturbed capfall craton. We can look at MOHO conversions and reverberations, which we're just talking about, the receiver functions. We also have done synthetic reflectivity seismograms, so they're not going to show, and travel time curves. But the seismic data indicate a very large velocity and density jump across the crust mantle boundary and implies a lowermost crust of intermediate or even felsic composition in the craton. So here's a receiver function we get from single event on the Kimberley array, some so-called nth root stack. Okay, the dashed line, this is the direct wave. This is the P-dash conversion. These are the subsequent, these involve S conversion. This is the 3P, and it doesn't show up, but the solid line is actually what we observe. And this is an extraordinarily good, I've never seen, this is, as far as I know, this is still one of the best receiver function signals that we've ever been able to come up with. What this tells us is that we can take these relative amplitudes of these converted phases, and we can calculate out from that the seismic density. So here's these amplitude ratios. This is what we get. This is the amplitude ratio we observe, and what it tells us is that the density variation across the MOHO is about 17%. We can do the same thing if take amplitude ratios here and get S-wave contrast. So we're looking at the right-hand one is the S contrast and S-waves across the discontinuity. This is finally the schematic of a MOHO structure beneath Kimberley, South Africa. What it shows is we have a Hartsbergitic upper mantle. We have a lowermost mantle. It's about 2.86 grams per cc. It's this Poisson's ratio, or very ordinary 0.25, typical of intermediate compositions. These are the velocity and density contrasts across it. What it says is that the transition across this MOHO is less than 0.5 kilometers. And that's a firm figure. So the average VPVS, let's a second here, let me go back. So what we're seeing, in essence, is finding a fairly felsic upper crust, and intermediate lower crust, maybe even felsic lower crust. So the crustal structure summary is that the VPVS for the crust, determined by two independent methods, is 1.74, which is very indicative of intermediate to felsic compositions. The minimum estimate for the increase in S-wave velocity and density across the MOHO, computed from receiver functions, 17% and 15% respectively. The transition zone across the M discontinuity beneath the Kimberley array is less than half a kilometer. And very importantly, the MOHO is virtually flat beneath the Kimberley array. We can say that it has a maximum allowable variation of less than 1 kilometer over the nearly 3,000 square kilometers of the array. So possible scenarios for a sharp and flattened MOHO. One is, and from most plausible to least plausible, thermal reactivation, large volume melting and flow in the lower crust in the late Archean. Could this be the Ventersdorp event? I don't know of any others that's there. Could be regional detachment of the MOHO, as observed in the Canadian lithosphere profiles across some Archean terrains in Canada. Or it could be lower crust electrolyzation, subsequent delamination, which I think is not at all plausible. So I'm going to end here essentially with questions that continue to bug me. If the continental crust was derived from a somewhat hotter mantle in the Archean, why is the crust not basaltic or even picritic in composition? Despite the occurrence, despite the occurrence of commoditeites locally, the Archean crust is in fact probably less mafic than the Proterozoic crust. How does this relate to the formation of the crust in the Archean? What was the role of large-scale flow in the lower crust in the late Archean? And what processes of continental agglomeration will produce a greatly thickened tectospheric keel without severely deforming the crust and the crust mantle boundary? Why doesn't everything look, in other words, like the Limpopo belt? And finally, this is just a 3D schematic summary, and I'll leave this up. This is the last figure. Top panel is this we put together for a cover of a volume, and this shows the kimberlite, the coating for the rhenium osmium modellages for the kimberlite pipes. This is the crustal structure underneath the array, and this is the mantle structure under the array. So with that, I will stop. Thank you.
Thanks so much, David, for that presentation. Well, now we have a few minutes for questions. If anyone wants to open off with a question for David.
David, did you manage to resolve what you thought might be the lower crustal composition beneath the Bushveld complex?
Beneath the
Bushveld complex.
beneath the Bushveld is no.
Okay.
It's yeah.
I mean, because it would be a
the seismic
surprise if
signals in
that
the
was...
Bushveld are really a mess, and it's really very hard to. What I can say is that it doesn't have compositions or moho structure anything like what is in the craton itself. It's been very much disturbed.
Which makes sense. I was just hoping that you might have been able to resolve whether the lower crust there is full of ultramafic
Yes,
cumulus,
that's a good question. Yeah, I've not been able to resolve that.
Any other questions here?
So Dave, this question of the flat moho has always intrigued us, but you know, Jesse mentioned this a little bit yesterday in the dome and keel structures in the Slave and Pilbara. But one of the key characteristics of this is, as with most cratons, is there's this big bloom of granites at the end of the Archean, basically, 3GA in South Africa. And, you know, we don't know why that really happens, but it strikes me like it goes along well with the flat moho in the sense of you had to mobilize a lot of this felsic melt out of the lower crust.
Yeah.
And so it means your lower crust had to be damn hot and probably pretty fluid. And it strikes me that that's a good opportunity to let it flow out as a nice flat pancake.
No, there's a lot of evidence that there must have been significant crustal flow. I mean, if you look at the Vredefort structures, which are, you know, that's this impact crater that essentially turned the crust on its up so that you could actually, in real life, study a cross section through the crust, and it looks as though it's been definitely remobilized. But my question is, how does that happen? I mean, where's the temperature pulse come from? Where thermal pulse come from? Where does
especially when you've got a cratonic keel below it that's the same.
Yeah, you've got a nice cold depleted cratonic keel, and how in the heck does that? Yeah.
So I was hoping you had the answer.
Rick, you know very well that 10 years ago, 20 years ago, we didn't have the answer, and we still don't.
Oh, yeah. Take it back here.
Well, I think the answer is that you melt the crust when you compress the craton. I mean, we've been exploring dynamic models and this, so has the Dan McKenzie group. And when you double the thickness of the crust, when you laterally compress these things, you melt it. And I think that, to me, really nicely provides a nice explanation for that type of behavior, because you essentially zone refine the crust, where that melting event causes the granite bloom, and so you take all the heat producing elements and you put them in the upper crust.
So those dynamic models, I mean, you've actually produced dynamic models that'll
you double the thickness of the crust. You essentially increase the sort of total area or volume of heat producing elements, and you can melt the crust.
And then everything.
Yeah, and if you look at, if you go around the world looking at cratons, a Neo-Archean granite bloom is a key feature of many cratons.
Yeah.
A slave craton is the type example of that.
Yeah.
All right, Lara.
So, this is on, yeah. So the problem, of course, there is that you have to get rid of that rustite somewhere. We don't see it, right? It's not in the mantle lithosphere. It's not at the base of the crust. It's missing. Well, if you're creating a granite, where does everything else end up? So the reason I bring this up is in part because my interest being flat slab subduction, the more we study those, the more that we see that they're actually really good at ablating whatever you need to ablate and then leaving other things behind, right? So if you wanted to get rid of a lower crust and supplant it with a mantle lithosphere. That's how you do it. Because it not only gets rid of a lot of the crust that it brought down with it in the process, it sort of snowplows everything away out in front of it and deposits it further on. And I know that the dynamics will be different in a hotter Earth, but if anything, that makes it easier because it means that you can still have enough heat to generate melting in the crust, but you can also just sort of supplant everything that you need to get rid of in the process and leave behind a sharp boundary. So it's the mantle lithosphere. Yeah. The rest side of the flat slab is lying underneath the crust.
Really?
Why not?
No.
We do know that, for example, in Peru, we have a bit of flat slab that's just stuck onto the base of continent now. It's just there, right? And
Yeah, but remember, we're bringing up all kinds of nodules up from here. We're picking up everything that's under there,
right,
and we're not seeing any evidence of a flat slab lying under.
well, remember, we're not
immediately
talking about
underlying.
an oceanic flat slab. We're talking about continent underlying continent, right, Jesse? I mean, that's the kind of thing that you're talking about when you have this imbrication, to call it subduction. Right? I mean, if you have this imbrication, which is maybe a better word than subduction, right? Because I'm not talking about oceanic plate. Well, I understand that, but the parts that you left behind have different seismic velocities than what we're seeing.
Yeah.
Then where is it? And
Yeah, but we don't. But the lower crust is not a refractory-looking crust. I mean,
that's
it's
just it. We
basically
don't see it seismically. It's gone.
felsic to intermediate in composition. It's a TTG crust. No, although actually there are enough crustal xenoliths that we should be able to tell. Rick, you know, I haven't followed the literature on the crustal xenoliths.
Okay. Yeah, granulite Faste's lower crust is depleted particularly in uranium. So they have, I mean, I'm generalizing here, but they have very unradiogenic lead compositions because the uranium's been taken out. So you're looking at relatively subtle differences. You're not talking about basalt and Hartsbergite.
Right. Well, I think we probably won't get a solid answer to this question yet.
All right, looks like Steve has a question.
Less a question than a comment. I want to thank Dave for coming out of retirement from 10 years to give us a talk on a subject that's dear to his heart.
It was probably obvious.
Rick,
anyway.
you can get ready to come out of retirement in 10 years too.
Right. Talk about the same thing, right?
But I'd like to ask you a historical perspective question with regard to Pascal and then the later type of resolution and more sophisticated broadband arrays. First, I have to make a comment that the biggest effect of the Pascal program was to bring Jan Dunlop here, who you hired as your secretary.
Yes.
If I remember correctly.
She was my first and only hire here at Carnegie.
That's correct. And she shared an office with the first Richard Carlson, because there was a Richard Carlson here who was a playwright, correct?
Yes, he was a playwright.
and didn't do much work because he was really writing his plays. And so that's why Jan succeeded.
Carnegie was an ideal,
yeah. And so the first Richard Carlson was replaced by the second Richard Carlson, who we're celebrating today. Well, you could try it out. So could you comment a little bit on the transition between the early Pascal type instrumentation and then the advent of tomography as from the Harvard group as an imaging technique, and kind of how it played into the timing of the transition between the Pascal arrays and the kind of stuff we see at the Kopval array. What drove the transition to this kind of tomography?
Well, okay, first of all, as far as DTM was concerned, the John Vandekar came as a postdoc, and he was at the time one of the architects of modern tomographic imaging software. I mean, he wrote the programs. Yes, Harvard had some, but they were, but Vandekar was really a driving force behind this, and he was the one who was initially responsible for putting together all of the package of tomographic imaging that we do here. And I think it's still his work, but we knew that the tomographic imaging was coming on right about, CAT scans were fairly new at that time also, and people were just realizing that you could, if you had enough crossing rays and all of that, you could actually find differences in velocities and structure. So ask me again, what was the chronology of Pascal? When Pascal came online, initially, none of the initial experiments were looking at tomographic imaging.
Yeah, right, exactly. So you're looking at basic crustal structure, right?
Well, crustal, but yeah, looking at velocity structure and discontinuity structure, yeah. So
I kind of wondered about.
This was.
You're the only one that could give a perspective on the timing of the change from crustal structure in Pascal to the more deeper, tomographic imaging.
Well, this Kopval project was really the start of that kind of imaging. I mean, there had been tomographic imaging before that, but sort of broad and very, large scale, 1,000 kilometer or several hundred kilometer scales. And this was really the first experiment that actually attempted to bring it to geological scales. Rick?
I just want to add one thing. Pearson global tomography. The audience is probably not aware of. So there's obviously global tomography of Southern Africa as well. But in arguing with one of our Australian competitors in this project, I will note that at the tomography that he was using, the Kopval craton is about 2 pixels of their image.
Yes.
So getting to the kind of resolution that could create certainly the lower figure there, you need the seismometers are a lot closer together than 1,000 kilometers apart, right? So, I mean, this is a transition from studying tomography at the global scale, meaning the planetary scale, and getting it down to a geological scale.
Yeah, to geologically meaningful scales, yeah. And I should mention also that actually this tomography, we can take this tomographic image all the way down and actually see the top of the South African, the African plume, South African plume. And that showed up very clearly in our tomographic images if you take it down to thousands of kilometers.
Okay, I'll just ask a real quick question because I don't know enough about geophysics yet. Do you have any is there any signs of either compression or extension? I mean, do you get anisotropy or anything like that that could maybe help resolve some of the differences we've been talking about?
Anisotropy would in this case, nothing that I studied did we do anisotropic measurements, but yes, anisotropy, as one of the subsequent speakers, Maureen, will tell you, is a very, very important measurement.
All right, great segue.
Thank you.
Our next speaker. Thank you, David. Thanks, David, and thank you everyone for your questions. Our next speaker is from Yale University, Maureen Long. Thanks for joining us today. She's going to speak about the geophysical constraints on the mechanisms of interplate volcanism from the high lava plains to eastern North America.
Just let me get mic'd up here. Thanks. All right, is that loud enough? I can be loud too. Okay. Excellent. Well, thanks very much, first of all, to Steve for putting this together and for the invitation to speak. I'm going to talk today about a couple of different case studies looking at mechanisms of interplate volcanism in continental settings. One from the western US and the high lava plains. So this is a picture of Jordan craters in eastern Oregon. This is part of every single inch of eastern Oregon that Rick and Bill and others have walked across. And then another case study in eastern North America. So this is a picture of Mole Hill, which is an Eocene volcanic feature in western Virginia. So I'm gonna, we've already heard in this meeting about interplate volcanism. So Dominique talked yesterday about plumes and interplate volcanism in an oceanic setting due to a mantle plume, and that's relatively well understood. We also have a very rich history of interplate volcanism in a lot of continental settings, and oftentimes the mechanisms for that are less well understood. So I'm going to try to play my movie. Yeah, it works. Okay, so this is an animation of the NAVDAT database over the Cenozoic. So this is looking at volcanism in the western US. And this purple line here more or less marks the plate boundary. So this is going through time here. And you can see that there's this very rich history of volcanism that's located relatively far away from the plate boundary. I'm going to try to play this one more time. There's a few great features here. One is that there's lots of volcanism along the margins of the Colorado Plateau down here as we sort of go through time. And then what you notice as the plate boundary evolves, and then right starting at about 16 million years ago, there's this big pulse of volcanism in the back arc of the Cascadia subduction zone, and that's what I'm going to focus on here. I will say that the first time I saw this animation or something like it, I'm quite sure that Rick was the person that showed this to me, and I was really quite blown away at just how much volcanism there has been during the Cenozoic in the western part of North America. So we're looking now at the Cascadia back arc. So just here's the tectonic setting. Here's the Cascadia subduction zone. The trench is out here. The Juan de Fuca plate, remnant of the Farallon plate, is subducting beneath western North America. So again, going back to about 16 million years ago, we had the outpourings of the Steens Columbia River flood basalts, often associated with the impingement of a mantle plume. So that's in the kind of brown here. And then since that time, 16 million years ago, there have been a couple of distinct volcanic trends. One in the Snake River Plain, then sort of leading up to Yellowstone. The rhyolitic volcanism of the Snake River Plain shows a pretty clear age progression where things get younger as you go up towards Yellowstone. And this trend is parallel to the absolute motion of the North American plate. So again, sort of easy to understand in the context of a simple model of a plate moving over a plume. There's also a trend here in the high lava plains of eastern Oregon, and this one is a lot more puzzling to explain because here we have again, the rhyolitic volcanism that gets younger going up here to the northwest, sort of culminating here at Newberry, right in the back arc. So this trend is oblique to plate motion, is a lot harder to explain in terms of a mantle plume mechanism. And another thing that's puzzling is in addition to these defined spatiotemporal trends in the Snake River Plain and the high lava plains in terms of the rhyolitic volcanism, there's also basaltic volcanism that's kind of widespread in space and time. And so it's sort of enigmatic what's going on with the HLP track here. So in order to answer this question, I was extremely fortunate as a postdoc here at Carnegie to be involved in the high lava plains project. So this was a big interdisciplinary project to try to understand mechanisms of interplate volcanism in the HLP. So this was led by Rick and involved a big group of people, including some of the people here in the audience. The seismology deployment was led by David and Matt Fouch, and myself and Lara Wagner, who were postdoc office mates at the time, were involved as well. So this is a map of the deployment. We deployed something like 120 broadband seismometers with very close station spacing, kind of a successor to the CAPVAL experiment, but even more ambitious in terms of numbers of instruments and dense station spacing. So here's the state. It's a little hard to see. Here's Eastern Oregon. Here's Idaho, Nevada, and then California. Here are some field photos, me having way too much fun driving my truck around in the mud and sometimes paying for it. And this is a photo of one of our stations, and I wanted to show this in particular. So we're powering the equipment that David showed pictures of, off a battery that's charged by solar panels. You see that we have this nice solar panel mount with a couple of fence posts and some PVC glued together. This is known as a Carlson frame. So this was designed by Rick Carlson, the mount system for the solar panels. And I have used this design on every single broadband deployment I've ever done. And my students all know that these, do we have enough Carlson frames? So we still call them Carlson frames. And they, when I remind them that they're named after Rick Carlson, who's actually a geochemist and not a seismologist, they get a big kick out of that. Okay, so the HLP project looked at a bunch of different interesting science questions, but the one that I was most interested in and most involved in is what are the present day patterns of mantle flow beneath the HLP, and how does that mantle flow field drive patterns of upwelling, melting, and volcanism? And so in order to answer this question, we looked at seismic anisotropy, which results from mantle flow and deformation. So these are measurements of shear wave splitting at this lovely, dense, beautiful array of the high lava plains. The sticks represent, the sticks are oriented along the fast shear wave splitting direction, which in this context you can kind of take as a proxy for mantle flow direction. And we found just beautiful, very consistent east-west fast splitting directions beneath the high lava plains. That was a little bit unexpected. It's not parallel to the absolute motion of the North American plate, which is what we see out here. It's also not parallel to the convergence direction of the Juan de Fuca slab, but instead it's parallel to the actually the direction of trench migration. So we have the trench out here, and that trench is actually migrating. The slab is rolling back. And so in order to understand that a little better, a piece of the HLP project was doing some geodynamical modeling using analog models in the lab. So this is work by Kelsey Trukin and Chris Kincaid at URI. They ran a bunch of experiments in their big tank of corn syrup simulating the mantle with realistic kinematics for the Cascadia subduction zone. And they showed that when they put in a model that had rollback and steepening of the slab, they got this sort of beautiful 3D toroidal flow field that beautifully matched our observations for shear wave splitting. So put some really good constraints on what that mantle flow field looks like. Just as a quick aside, that the data set that we collected during the HLP project has truly been a gift that has kept on giving for me. I've actually been working on HLP data on and off for the last going on 15 years now. And we've actually used the data set in my group quite a bit when it comes to developing more sophisticated sort of techniques for imaging anisotropy in the upper mantle. And so, we have several recently published or in prep papers that continue to rely on this data set. This is a really nice figure that one of my grad students, Jonathan Wolf, made about 2 weeks ago. He's doing global wave field simulations with arbitrary anisotropy included, and he's using the HLP data set to benchmark some of his models. So it's a truly remarkable data set, and we're still doing some amazing cutting edge science with it, almost 15 years later. Okay, so back to the HLP story. One of the things that we did with the course of the project that I thought was one of the most exciting parts of it is we did a very nice and kind of careful synthesis of all of the different constraints on mantle flow and depths and temperatures of melting that we got from all of the different components of the project. So that includes some of the geophysical imaging. Here are a couple of tomography models. David gave a very nice intro to tomography. This is a surface wave-based model from Lara's work. This is David's S-wave tomography, body wave tomography model. So we took the tomography, we took the constraints from the geodynamical models, compared it to the anisotropy observations, and then we also looked at the geochemistry and petrology of the rocks. So these are some constraints from thermobarometry of basalts that constrain the depths and temperatures of melting, done by Christy Till and Tim Grove. And we put all this together in what I think is actually a very nice kind of synthesis paper that proposes a conceptual model for mantle flow and generation of melts and volcanism that is consistent with the geophysics and then also all of the other constraints. So our model invokes a phase of steepening and rollback of the subducting slab starting around 20 million years ago. It kind of sets up this three-dimensional flow field. There's a pulse of a large amount of upwelling right around 16 million years ago. And then that kind of kicks off the time progressive HLP trend. And so that we continue to have this toroidal flow field that includes a substantial component of upwelling, decompression, melting, and producing the volcanism. So I think a very nice example of how synthesis across these different disciplinary constraints can really lead to progress. So now I'm going to switch gears and talk about the eastern US. So we're moving now to a very different tectonic setting. Instead of a subduction zone back arc, we're now thinking about a passive continental margin. So this is, the last major tectonic event was 200 million years ago with the breakup of Pangaea. And we're looking here in the central Appalachians. This is a figure from work by Sarah Matza and others. And this shows in sort of map view the distribution of a bunch of volcanic products, bimodal, but a lot of basalts of actually Eocene age. So these are dated to 48 million years ago. And this is, of course, surprising because you don't expect to see volcanism on what was then a 150-year-old mature passive continental margin. And yet there we are. Just to orient us, so this is, of course, a map, but in addition to the geography and the state lines, this also is shows the colors are from a tomographic model. So this is a slice through the mantle at 200 kilometers depth showing S-wave velocities. And as we learned from David's talk, the red colors indicate slow anomalies. And you can see there's a very prominent low velocity anomaly in the upper mantle today. This is known as the Central Appalachian Anomaly, and it's co-located with these unusual Eocene age volcanics. So I was part of a team that wanted to understand better what is the detailed structure of the lithosphere beneath this region and what were the mechanisms for this intraplate volcanism. So I was involved in a passive broadband seismic deployment like we've been hearing about called the MAGIC experiment. So we deployed a dense linear array across the Central Appalachians. Myself and Maggie Benoit were the PIs on the seismology component, and then Rob Evans at Woods Hole also deployed magnetotelluric observatories. So we have constraints on electrical conductivity as well. So we went right across the Central Appalachians. This star here is Mole Hill. I showed the picture on the first slide. And again, we're interested in the architecture of the crust and lithosphere, the velocity structure in the upper mantle. And ultimately, we want to come up with a model for why we had this episode of intraplate volcanism during the Eocene. So a couple of field pictures. Here's me leaning on the Carlson frame. And then this is me and one of my students building a barbed wire fence to keep the cows out. We had one of our stations in a cow pasture. And I will proudly say that I learned to build barbed wire fences by working on the HLP project and honed my barbed wire skills out in the HLP. If you need a fence, I can build you a fence. So we did a bunch of different analyses on the MAGIC data, and I don't have time to talk through all of it, but we measured shear wave splitting and documented a transition from these kind of more northeast-southwest fast directions here to more east-west fast directions in the eastern part, and this transition is located right where we have these Eocene volcanics. We did receiver function imaging of the crust and lithospheric mantle. We looked at seismic attenuation and documented a really striking high attenuation anomaly right beneath the mountains, right, close to where these Eocene volcanics are. And then Rob and his collaborators did an electrical conductivity model. So the major takeaways for the purpose of this talk is, number one, there's this transition in shear wave splitting, which might indicate kind of a local disturbance in the mantle flow field, but also the lithosphere is thin. We have several, I would say 3 independent lines of evidence from electrical conductivity, attenuation, and then S to P receiver functions, which are not on this slide, that the lithosphere beneath the mountains today is thin. The LAB is probably at about 80 or 90 kilometers or so. So basically, it looks like a chunk of the mantle lithosphere beneath the origin has been removed. We put this together, and this is, again, something I'm really proud of. We put together the constraints that we got from the MAGIC imaging with work that others had done, doing tomographic imaging of the eastern US, mostly from Earthscope data, and then as well as some other constraints I'll talk about on the next slide. this is a very busy set of figures. This is from a paper published last year with a long list of co-authors, including Lara Wagner, who made these figures. And this is synthesizing basically all of the geophysical constraints all together. Here's our electrical conductivity model. Here's our tomographic model. This is an estimate of where the LAB is from receiver functions. Here's our attenuation anomaly. And then here's our shear wave splitting measurements. So we were able to put all of these geophysical imaging constraints together. And then we also thought about constraints from, sort of multidisciplinary set of studies. This, again, is work by Sarah Mata and collaborators looking at the geochemistry and petrology of these Eocene volcanic products, but also there's actually a co-located pulse of interplate volcanism in the late Jurassic, so they looked at those rocks as well. They did thermobarometry and were able to show that on the basalts, we're able to show that the melts had equilibrated at roughly 80 to 90 kilometers depth, right where we would put the lithosphere-asthenosphere boundary. And then we also looked at constraints from geomorphology. So we collaborated with Eric Kirby, who did stream profile analysis, and were able to come up with an erosion rate model sort of calibrated from cosmogenic nuclide dating. So this erosion rate model sort of throughout the Central Appalachians, they were able to show that there's this kind of like bullseye of enhanced erosion rates right where we have the geophysical anomaly. So again, this we sort of put all of this together in a synthesis paper that came out last year. We put all of these constraints together and then said, okay, what kind of models for lithospheric loss and partial melting and volcanism could possibly explain this range of observations? So we looked at models that included, thinning of the lithosphere through thermal ablation, delamination type models where we lose some lithosphere through a gravity-driven Rayleigh-Taylor instability. We thought about, sort of edge-driven convection type models or small-scale convection type models. And then we thought about models that invoke a mantle plume. And for each of these conceptual models, we thought about the full range of predictions that they would make and compared them to our geophysical and petrological and geomorphological observations. So this allowed us to come up with a preferred model that actually invokes 2 episodes of lithospheric removal, one during the late Jurassic and then the more recent one during the Eocene. Our preferred scenario is that, well, we lost the lithosphere perhaps through thermal ablation, but I think more likely through, again, this sort of gravity-driven Rayleigh-Taylor instability type model. Following that lithospheric loss event, we had upwelling return flow that led to decompression melting and the production of these Eocene magmatic products. And then since the Eocene, the system has sort of evolved to where it is today, where we maintain this thin lithosphere, we think by having sort of small-scale mantle flow here that actually is continuing to produce partial melt. We think that partial melt is present, again, with a very thin lithosphere-asthenosphere boundary around 80 kilometers or so. And that explains the tomography and the attenuation signature and basically all of the geophysical observables. Okay, so what have we learned about interplate volcanism? So I hope I've convinced you that geophysical imaging has a lot to say about this problem. Beneath the HLP, we think that the upper mantle flow field is 3-dimensional. It's driven by slab steepening and slab rollback, and that this can explain the patterns of upwelling, decompression, melting, and volcanic activity in the HLP. Beneath the Central Appalachians, we think there was actually multiple episodes of lithospheric loss, likely via Rayleigh-Taylor instability, with the latest one during the Eocene, and that this upwelling, return flow, decompression, melting led to the volcanic episode, and then we have small-scale mantle flow that's maintaining the thin lithosphere that we see today. And then finally, I hope I have convinced you that the integration of geophysical images with constraints from geochemistry, petrology, geodynamics, and geomorphology really provides a very powerful strategy for thinking about the problem of interplate volcanism and other problems as well. So I will just end with a huge thank you to Rick. I think it's probably clear from this talk that the ethos of cross-disciplinary collaboration and integration that I learned from Rick and others on the HLP project has been hugely important to my career and to how I think about scientific problems. So thank you for that. And also just to thank you, Rick. I was not officially your postdoc, and I'm a geophysicist and not a geochemist, but I've really benefited from your mentorship. You've been a model for me as a scientist, and you've always been a booster and cheerleader for me. So thank you very much for that. And I'll stop there. Thanks.
Maureen, really great synthesis of geophysical data sets with other observations. So I think we have time for a few questions. Let's start with Roberta.
Thank you. What a wonderful talk. Thanks very much for that. So the Appalachians were a while ago. I mean, the mountain building event was a while ago.
Yep.
So what caused this Rayleigh-Taylor instability to form in the first place in the Eocene?
You're like, nice story, Maureen, but why? Yeah, no, totally. I mean, this keeps us awake at night still, right, Lara? Like, I'm pretty happy with the model we have, but it doesn't answer the actually very fundamental question of why this part of the Appalachians? If you look at, I'll flip back quickly to the tomography, there are other regions, sort of notably, this is actually where my ongoing field project is up here in New England, there are other regions of the eastern North American margin that have a geophysical anomaly. They don't have, well, the same history of interplate volcanism, although there is a bunch of history of interplate volcanism here in New England as well. So I think you've articulated the big outstanding question. Why is it localized? Why during the Eocene? What's controlling the timescales of this? Is this a sort of a process that is kind of something that happens as mature passive margins kind of evolve through time? So is this something unusual and very specific to the Central Appalachian? So we don't know. I mean, I think there is almost certainly a role for inherited structure. That there was something about either the Appalachian collisions or the rifting and breakup of Pangaea that sort of seeded a lithospheric instability, but exactly what and why that's the next question. So you've asked a good question that I can't answer, but we're thinking about it.
So yeah, excellent talk. And we read, Laura and I kind of co-led this paper in one of our reading groups, and I did the petrology part, which was kind of thin, and she did the geophysics, which was very thick.
Right,
and
fair enough.
So we didn't think of this at the
That's
time.
what happens when geophysicists write your synthesis papers.
Right. So we didn't think of this at the time. I didn't think of this at the time, but since this started in the Jurassic, I mean, what about a beginning of rifting to open the Atlantic that kind of missed where the rifting happens now, but sort of started, the upwelling started a little bit to the west, and then it created damage in the lithosphere, which, and then it didn't succeed in rifting there, moved to the east. Then there's residual damage that then gets reactivated at a later time.
Yeah, I think that's extremely plausible. Yeah. So and teasing apart whether it was a rifting associated event versus Appalachian orogenesis, is tough. But I think that's extremely plausible. There was something either about the mountain building or the breakup that seeded an instability that then was later, popped off later and produced the volcanism.
Maureen, great talk.
Yes.
Fantastic. I love these images in connection with geology. But I want to go back to Dave's talk in the sense of what does the MOHO look like under this Virginian volcanic field?
So glad you asked. So, and I have it on a slide. So here it is. So these are P to S receiver functions, the exact same type of data that Dave talked about. So red, so here the red is a positive velocity contrast with depth. So the MOHO is here, extremely thin out here beneath the coastal plain. There's a very sharp step in the MOHO. It deepens quite a bit beneath the mountains. Now, Mole Hill is here. So it's not, when I first saw the MOHO step, I was like, sweet, we have an explanation for where but it's actually the melt came through the thicker part of the crust, which I'm not quite sure what to make of that. Deep MOHO here, and then this is an entirely different part of the story, but super deep MOHO beneath central Ohio. Who knew? This is, I think, the root, a root of the sort of Grenville thickened crust during the Grenville, but no topography here, and yet the Moho is at 60 kilometers. Again, different part of the story, but yeah, this is basically what the Moho looks like. It is not the beautiful, flat, uniform Moho of the Archean craton. It's definitely, I think, shaped very much by Appalachian.
But it looks to me like it's both a strong signal, so big velocity contrast, and fairly flat over the area where the eruptions have occurred.
Yeah,
so,
yeah, that's fair.
Yeah,
that's fair. Yeah.
All right.
Yeah, Lara, do you want to jump in? Yeah.
Yeah, so one of the other things that keeps us up at night with this particular project is that all of the tomographic images show a fast crust all the way down to the Moho.
Yeah, I didn't mention that.
Which is really problematic
Yeah,
because you have this low velocity region underneath an Eocene volcano. Now, if you want to connect those dots from the modern to 50 million years ago, you're suggesting that you have partial melting sitting directly below the crust for 50 million years.
Yeah,
And
and
somehow
we know
that
that
has
there's
failed.
partial melt there. Yeah.
How does that fail to reduce the shear wave velocity
Yeah.
of the
So
crust?
why is the crust relatively
It
fast and you
seems
don't see any
impossible.
anomaly? Yeah.
And what it suggests, I mean, the one thing that might suggest, and this actually came up in our reading group discussion, is that what we're looking at there is not a thermal anomaly. In other words, this isn't decompression melting. Maybe it's some sort of a compositional melt. And then carbon came up as a possibility as the latest, trendiest way to melt things at sort of mid-lithospheric depths. I don't know if that's possible, but it would give you the advantage of coming up with a low velocity in the mantle that isn't associated with the thermal anomaly that over the course of 50 million years should have percolated into the crust. So,
An
yeah,
interesting hypothesis to think about.
it's a problem.
If we ask questions long enough, we're going to air all of the dirty laundry and unanswered, unresolved problems with this. Yeah, I think that's right. And much as I like the idea, we've done, this is not published yet, so I got to write it up this summer, but we've done some pretty detailed, measurements of just travel time residuals and then modeled them together with the electrical conductivity and the seismic attenuation, which also gives constraints on this. And I think you need a temperature anomaly. I do. Say again? Well, melt, yeah. So if there's partial melt, but it's from carbonization or something. Yeah, maybe. We'll actually I will revisit that in light of this kind of hypothesis. So, do you need to kick me off the stage? Okay. How are we doing?
I think
on time?
we had a comment in the Zoom, and then I think we had maybe one more question from Jesse in the audience. Maybe we'll do that question
awesome.
first. And then
All right.
comment. All right.
Thanks, Maureen. That was really interesting. What's driving the geomorphological expression of this? Is it added heat to the crust, or is it removal of this like deep, dense lithospheric root?
This is another part of the story that at this point is sort of still like, wow, interesting correlation. And yeah, I mean, there are a few ways you can do it, right? Yeah, you get rid of a bit of dense lithosphere, and you have kind of a response to that. The timescales don't work particularly well, given that we know from the volcanism that this happened during the Eocene. Our geomorphology collaborators tell us that the time scale for that response should be something like maybe 10 million years and not 50. If there is a component of sort of ongoing small scale like upwelling and mantle flow, there might be a kind of a dynamic component to it. So I think those are compelling hypotheses, but we don't really know. That's another thread of this that I think we need to do a lot more work on. Precisely what is the nature of the connection between the enhanced uplift rates and what's going on in the mantle. But those are some potential ideas.
All right, we'll just finish with the comment in the Zoom. So this is from Frank Dudas, I apologize if I pronounced that incorrectly. Molehill has spin peridotite xenoliths, which with large spinels whose Fe3, Fe2 ratio suggests an unusually oxidized mantle source, more akin to subduction-related environments than the stable mantle environments. There are also scattered kimberlites through central and western Pennsylvania. I think these are older, but don't remember the
Jurassic,
actual ages.
But yep.
So there are magmatic records of multiple post-Appalachian events.
Yeah, so the not so passive, that passive margin, right? Yeah, no, the Molehill rocks are wild. I mean, I am not a petrologist, but I've hiked up there, and you just look at the rocks, and you're like, what the heck am I looking at? Like, there are like visible, you know, there are crustal and I think mantle. Are there mantle xenoliths? Definitely lower crustal. And you can just see, you know, there's like sandstone xenoliths in these rides. It's crazy. Sorry, I got excited about the rocks and now I forget the question. But yes, there's a very, you know, extensive record of post-rifting magmatism on this passive margin, and I think we are just scratching the surface of what we need to learn about how it all worked.
All right, thanks so much.
Thank you. Yeah, of course.
All right, our next speaker here is going to be Diana Roman from Carnegie. She's a staff scientist and the H.O. Wood Chair of Seismology, along with Lara. Diana today is going to be talking about a quantitative temporal look at how volcanoes work.
Okay, just a sec. Act together up here. Oh, there we go. Okay. Okay. First of all, thank you, Steve, for this opportunity to basically present a tribute to Rick's contributions to volcanology at Carnegie. Maybe you know, maybe you don't, but actually volcanology has a very long history at Carnegie, going back to the early 20th century and the work of Frank Perret, Harry Oscar Wood, Carnegie's role in the founding of the Hawaiian Volcano Observatory, and then going through in previous decades, recent decades, the work of Alan Lindy and Selwyn Sachs with the strain meter program and several amazing deployments on volcanoes around the world, looking at strain changes preceding eruptions. But really, I think Carnegie is going through a bit of a renaissance in volcanology right now. That's very much to Rick's credit. And so I think what I wanted to do in this talk, and the reason for the very vague title, is sort of give you a general overview of kind of what volcanology at Carnegie is today. And really, I think, try to highlight a couple of things that Rick in particular has supported, which is our postdoctoral program in volcanology, which is just phenomenal and really brings us the kind of intellectual diversity that you need to do cutting edge research in volcanology, because it is a very multidisciplinary field. And also our diverse equipment pool. And so Rick has also been very instrumental in helping us to acquire a very diverse suite of instruments that we can use to study volcanoes worldwide. So basically what I'm going to do in this talk is go through about maybe 5 or 6 recent results from various group members. And I'll go through them, you know, very quickly, 1 or 2 minutes each, and hopefully enough to tempt you to read the papers and maybe talk to the postdocs, but I won't have time to go into nearly as much detail as they all deserve. But what I want to do in showing you these sort of snippets of recent research is kind of demonstrate again, you know, how our postdocs bring us the ability to do really multidisciplinary work. We're moving into very quantitative understanding of magmatic processes. We're working on a wide range of spatial and temporal scales. And we're really trying to get at both fundamental understanding of how volcanoes work, but also, you know, we sort of walk the line between fundamental research and applied. You know, a lot of our work really does have important implications for volcano monitoring and accurate and comprehensive forecasts of eruptions. Okay, so I've also listed up here just the core group of volcanologists currently and our recent postdocs, but I haven't listed people like Lara, Dr. Flatslab, who we occasionally manage to tempt into working with us. So everybody dabbles in volcanology these days in the geophysics group. Okay, so the first two studies I want to talk about kind of relate to this older idea that actually goes back to my PhD of us seeing basically a very localized ephemeral change in the crustal stress field as we get magma intruding into the crust, both prior to eruption and often during intrusions. And so this is kind of just a little cartoon version of what we sort of see very frequently when we look at fault plane solutions of volcanic earthquakes. We see that we have a regional stress field where maybe maximum compression is like that, and that we actually see that the fault plane solutions rotate by about 90 degrees as basically the dike opens up. And this is a little example of that from an eruption in the 90s at Spur, where you see this nice flip before the eruption and then going back and then flipping during a sort of intrusion event that followed the eruption and then back to normal. So this is something that it's kind of neat, but what do you do with it? And so for a long time, it's been sort of qualitative, and we've had a sense that when we do see this occur during episodes of volcanic unrest, it tends to be when we have high bulk viscosity magmas. But we also have a sense that the strength of the crustal stress field, so the deviatoric stress field, the difference in magnitude between sigma 1 and sigma 3, also play a role in whether or not you see this occur prior to an eruption. So it's been kind of, what do we do with it? But fortunately, in 2018, Kilauea actually did one of the best natural experiments we could hope for to allow us to look at this concept that this actually is viscosity controlled by erupting a range of different bulk viscosities throughout its 2018 Lower East Rift Zone eruption in basically the same ambient tectonic setting. So we could really kind of get at when the stress field rotation was occurring during the eruption and trying to link that into to the viscosity of the magma that was going through the system at the time. So this is a very complicated figure. Again, I said I'm not going to go read the paper, but what the point is that we do see the stress field rotation occurring mostly when we get the higher viscosity melts coming through, and then we really see it go away when we have the more kind of primitive standard Kilauea basalts. And so what we did with this that was super cool and actually was a collaboration, this piece of the work was led by Arianna Soldati at North Carolina State University, but also involved former GL postdoc Don Dingwell, was we were able to look at the bulk viscosity experimentally and model constrained for different phases of this eruption where we didn't see the rotation and where we did see the rotation. And at Kilauea, at least, we were able to put a pretty tight constraint on what the viscosity threshold needs to be in order to create this rotation. And so this is, you're wondering maybe why, but this is really important because we need to know what's coming down the pipe. And in fact, the hazards during this Lower East Rift Zone eruption, which was in a populated area, were very much dependent on whether it was erupting something that was very thick and forming kind of localized lava ponds, but trapping more gas and therefore potentially more explosive, versus more low viscosity stuff that would create long run out lava flows. So this actually is quite important, and this actually gives us now potentially a tool to kind of know what's coming up the pipe and what the hazards might be at Kilauea. And then this actually expanded, this is unpublished, but where we're going with this is trying to get into a global viscosity threshold for rotation. So this is work that Arianna put together that we're trying to follow up, where we're trying to figure out, does this threshold that's defined at Kilauea really apply globally when we look at other case studies that rotate and don't. But we still have in here, this is a noisy data set because we still have the tectonic stress problem. We know that that's also in effect. So the second study I want to show you is actually a paper that just came out this week by our current postdoc, Yan Zhan in GRL, where he did a really elegant job of kind of taking a case study, learning seismology, doing the fault plane solutions. Yan is actually a numerical modeler, finding a really nice 90-degree stress field rotation during this eruption at Augustine in 2006, and then looking at kind of the time of when that rotation occurs, and then trying to really link that quantitatively into basically three potential contributions to the stress field and what we might be able to say quantitatively about the different forces acting in the volcano. And the geochemists are going to love this next one. I was blown away when Jan came to me with this figure, but he basically ended up creating this nice phase diagram of different contributions from edifice loading, tectonic forces, and dike opening, and actually looking at where the triple junction of the transition of what we see expressed in the seismicity, where that is depending on the density that we assume. So this is actually really getting us nicely into sort of quantitative, potentially measures of what dike overpressure has been reached when we do see the onset of this rotation at different tectonic stress conditions. So this was really exciting, and I think really a major step forward in this type of work, from bringing it to something that we can actually use in models in forecasting space. Okay, so those were two studies where we were working on data that we'd gotten from our volcano observatory partners, but we do a lot of our own field deployments as well in the volcanology group. And so this really quickly was a project that was a former postdoc who's now at NASA, Kathleen McKee, who came to us as an NSF fellow with a really elegant proposal to deploy seismometers and infrasound sensors at Stromboli volcano to basically quantify this model, this long-standing model of Strombolian activity and its associated seismicity. Basically this idea that Strombolian eruptions are a gas slug moving up through the conduit, generating what we call a VLP earthquake on their way up, and then bursting at a free lava surface and generating an explosion. So Kathleen wanted to kind of do an accounting of the volumes from both an acoustic and a seismic perspective. However, what she actually found, which was very frustrating but very exciting, was that during our deployment, almost none of the VLPs actually corresponded with explosions when we looked at acoustic data corresponding to the VLPs. And so this actually led to, I think, in hindsight, a pretty obvious model that says that, in fact, the longstanding mechanism of Strombolian activity is not applicable to volcanoes like Stromboli, which are very hydrous, and probably are forming shallow mush plugs because of decompression, degassing-induced crystallization, and that really what you're seeing is the VLP is occurring, but this is kind of acting as a mechanical filter on the gas slug that then comes through, and actually very few of those VLP, those gas slugs, actually result immediately in explosions. So this is really quite different than what she started out with. It's fighting its way through the review process at GRL right now, so stay tuned. It's a bit controversial because it upends a lot of thinking about VLP seismicity. And I should note, just here's some field photos. This was actually the first international deployment of our quick deploy boxes, which is something that Lara is going to talk about next, and something that Rick has been a big supporter of, I think because he's seen how difficult it is to do field seismology, and he cheers on anything that makes it easier. So Kathleen was kind enough to let us use her experiment as a guinea pig for these boxes. Okay, so we come back from doing field work. In this case, it looks beautiful, but sometimes we come back and we're tired and it's been in the rain, and you can't do seismology from space. But one other thing I wish I could do sometimes after I do field work is remote sensing. So a lot of the work of Carnegie Volcanology is actually based on using satellite data to study volcanoes. And so this is another very recent, I think just in the past month, paper that came out by Lara Shreve. This is actually work from her PhD at IPGP, looking at the end of a very, very long-lived eruption that, at Ambrum volcano, which was until this, the end of this eruption, the highest SO2 emitter on Earth. So Tara did a very elegant study using gas emissions from satellite, radiation from satellite, and deformation from satellite to basically show that the long-standing trend of deflation at this volcano actually paused shortly before this final eruption that led to the end, and that actually the volumes of what was erupted correspond perfectly to a new intrusion that basically turned off this long-standing deflation trend. So this is a really nice mass balance accounting that did work out very well and sort of shows the power of satellite remote sensing, although it would have been great to have seismic data for this as well. So the last one I want to talk about is a bit of a star-crust project. And it was actually supposed to happen at Ambrim in 2019. We were trying to go to the most dependable lava lake on Earth. And of course, as you can see, the volcano had other ideas. So that was problem number one with this last one. So instead, we went to Villarrica volcano in Chile. And we started this deployment in January 2020, got it half deployed, aiming to go back in March 2020, finish it, let it run. COVID had other plans for us. But this was a really, I think, this is, again, another towards forecasting. This was a really high-risk effort to use continuous gravimetry to try to understand, to detect changes in lava lake levels or gas content, basically that lead to explosions. So these are tourist volcanoes. Villarrica is full of tourists who are coming up to see the lava lake. It's very hazardous because it does occasionally shift from having this cool little lava lake into a major explosion. And so we really need tools to be able to say when something is coming up the pipe that might result in that transition. So the idea here was to deploy a continuous gravimeter as well as various other sensors that would give us constraints independently on what the volcano is doing to try to test the idea of continuous gravimetry as a very high sensitivity monitor of potentially these transitions. And so I just got back. Tara and I were both in the field 3 weeks ago in the snow, pulling the instruments out finally. And so we don't have results yet, but just as a hint, we didn't want to show the gravity yet because it's still being reduced. But as a hint, we did find that we, back in 2020, managed to record a nice thermal anomaly from satellite. And then the new multi-gas instruments actually pick up a really nice spike in CO2 a couple weeks later. And so this is the type of thing where we're hoping that the gravity data will help us know what's going on here. Was this a deep slug of gas that kind of elevated the lava column from beneath and then came up through and then was emitted at the surface a few weeks later? So this is really exciting, and stay tuned for that one. Okay, so I just wanted to end with a couple where we're going next. So the thing about field geophysicists is we like our labs to be empty. We're not happy when there are instruments sitting on the shelf. And so the lab has clearly been very empty. We've had all of our kit at Villarrica for a couple of years. And the kit is coming home, but it's going straight back out again, thanks to Rick in a couple of cases. The seismometers are going out to the Aleutians this summer to collect some additional data, to test a hypothesis, fairly controversial hypothesis that there is actually a large caldera, potentially the largest caldera in the Aleutians, in an area called the Islands of the Four Mountains. So Rick has been very generous in giving us the seed funding to go out and collect additional data to try and test this idea and potentially gain funding for a much more comprehensive study. And then Rick has also been really instrumental in getting us the 2 gravimeters. And these are not kit that every volcanologist has. And so we're extremely fortunate to have 2 of these instruments. And the gravimeters are just back from Chile, and they are now going out to South Sister this summer to be part of a collaborative NSF-funded proposal to look at magma dynamics, the long-term history, and the current unrest at the Three Sisters complex. So that's pretty exciting, so stay tuned. So I wanted to end by, I was looking yesterday for some photos that kind of illustrated Rick and geophysics, and this was, I came across this one, and there's Rick in the background here, and this was a photo that I took about 2 minutes after the 2011 Mineral Virginia earthquake. And you can see all of the geophysics group at the time rushed outside, and Rick joined us almost instantly and started asking questions about, tectonics and what's going on. And I think this just illustrates that Rick truly is a geophysicist at heart. So Rick, I wanted to thank you again for all of the support of volcanology over the years, for your support of me personally. It's been a privilege to know you as my colleague and to have you as director. And I wish you and Sonia the greatest retirement. And thank you for everything.
Thanks, Diana, for summarizing some of the work in volcanology that's being done at Carnegie right now and has been done in the past. So do we have any questions in the audience? Yeah, Rick.
Thanks, Dana. What a great summary. Can you help me understand how magma viscosity affects dike overpressure? Is it because when it's in viscous, it has other places to go? Or?
Yes. That's the million-dollar question. And so is it that a higher bulk viscosity is simply impeded from flowing into the tip and has to go out? So, we talk about overpressure as a kind of somewhat vague thing, but I think what we're also seeing is that what we may want to look at is different directions of pressure, that it's not just a pure fluid. This is a very complicated three-phase thing, and it may actually be moving outwards more than it's moving upwards, and that may be a function of something just like its overall bulk viscosity. It may be a dynamic process like shear dilatancy, where it has to move out to get the crystals around each other under Poiseuille flow. We don't know. This is the big question, and Ariane and I are starting to work on some proposals to start getting at some of these questions.
I think we have a question in the Zoom. All right, this is from Francis Jenner, Reshka, and Fran. Villarrica magmas are anomalously CU-rich compared to other Chilean magmas. Is there anything unusual about this volcano compared to neighboring ones that you have found so far?
Well, it's always erupting, and we spent a lot of time talking about this, and actually this relates back to the caldera story. So Villarrica is on the edge of a caldera, and we often see that weird volcanoes like Villarrica that are kind of constantly doing this low-level thing often are located on the edge of calderas. But geochemically, I don't know. I would love to have a chat, friend, but to me, the first thing is, why is this one volcano kind of always going, and why does it have this long-lived lava lake and explosive activity compared to its neighbors, which wake up every few decades to centuries to millennia?
All right, thanks. Another question in the back.
Fascinating. If you want to keep your lab empty, no one's ever seen a kimberlite erupt, and there's this problem where they all seem to stop at about 50 million years ago. But recently, there's a really quite remote location called the Igwizi Hills in Kenya, where the kimberlites are so young they're hard to sorry, Tanzania. Thank you.
Yeah.
Are very hard to date, probably 5,000 years or less. I mean, it would be really interesting to put a bunch of instrumentation around there and see if there's any indication of the next kimberlite.
Ooh.
I'll come with you, by the way.
Yeah. Let's talk. That could be quite interesting. Thanks.
All right, if there's no more immediate questions, we might move on to Lara. Thank you, Diana. All right, so the last speaker in our field geophysics session is going to be Lara Wagner, who has been mentioned a few times in the previous talk as a co-author. She's also an H.O. Wood Chair of Seismology here at Carnegie, and she's going to be discussing new directions in seismic instrumentation.
I'm never really sure where to put this thing. Let's see. Can you hear me, Bueller? Okay. Great. So Oh, right. Um, so we've heard a lot of great science that came out of not just the geophysics that we do here at Carnegie, but in particular in doing it in a multidisciplinary fashion with the kind of science that Rick has always embodied. The fact alone that we have a geophysics session in the retirement symposium for a geochemist speaks really to itself. And so while I may be not suggesting that you're Superman, I really do appreciate your deep vision for how to do science. So, harkening back to David's talk at the beginning, Carnegie has a long history of instrumentation across all disciplines, whether we're talking about telescopes or all of the toys that you have over in the cyclotron building. But in seismology, Carnegie has really led the way. So I have actually a copy of this old report, the initial idea for Pascal. And 2 of the 10 standing committee members that put this report together were from Carnegie, which I think is a pretty impressive history. And in the 38 years since Pascal was established, tens of thousands of temporary portable broadband stations have been deployed. This map is almost certainly not comprehensive. It's surprisingly difficult to get that list together. But among these tens of thousands of stations, of course, include the high lava plains deployment, which we were talking about earlier, and then also the South African seismic array, both of which you've heard a lot about. And these stations are installed by armies of PIs and students and postdocs over the decades. And I'm proud to say that Rick Carlson was one of us. So there's a picture of him. I was complaining yesterday that I hadn't actually seen a picture of him in the field doing seismology fieldwork. And of course, MA jumped in for the save together with David James and provided me with this photo. And, but you were there. And in the corner, of course, the Carlson frame, which has already been mentioned. Rick's focus on the big questions and using whatever tools necessary to get at them is an inspiration to me. So whether you're looking at planetary formation using astronomy and astrophysics, planetary evolution using geochemistry, cosmic chemistry, and geodynamic modeling, all of those have to eventually lead to the planet that we have today. And we know what the planet looks like on the inside from seismology and associated mineral physics that tell us how to interpret the seismology. And Rick understood this, and he understood that if we really want to get at understanding planets, you need all of it. You need all of it. And that vision is truly inspiring to this day. I won't be talking a lot about specific science questions, but just as an example, we've been hearing for 2 days now about the importance of volatiles at all stages of these processes, right? Where did they come from? How did we hold on to them? Where are they now? How have they affected Earth's geochemical evolution? All the way up to things like the biosphere. Do we need plate tectonics to cycle volatiles in order to maintain our atmosphere and therefore life as we know it? These are really big questions. And all of those require this multidisciplinary approach. Seismology's role is to tell us what exists today. So we can study modern analogs for processes that we think have happened over time, whether that is, how is it that we get water into rocks to be able to transport them to depth? Where is that water released, and what types of metasomatic effects does that have in terms of forming continents and forming planetary differentiation? And then how deep does that water cycle go and over what timescales, which are projects that we've had some really great recent multidisciplinary efforts to work on that combine everything from metamorphic petrology to seismology to diamonds to earthquakes, you name it, it's all across the map. So it's a fun place to work here. We know where the water is from seismology, in part because we are getting an ever clearer picture that the release of water from slabs are responsible for the formation of earthquakes. So if we can locate the earthquakes, we can locate where the water is coming out of the plate. We've talked a lot, you've heard a lot about this before, that imaging seismic velocities in 3 dimensions using tomography allows us to understand what these structures are at depth. That goes beyond just knowing what the shapes are, but also having an understanding of where the water is, water reduces shear wave velocities. And increasingly, as the mineral physics get refined, we're learning that things like VP/VS ratio, which used to be used as a hallmark for the presence of water, is actually a much better indicator of the presence of silica. So improving our understanding of exactly how these elastic parameters work, how they respond to pressures and depth is something that we continue to look at. And so in the end, we come up with these images that have improved vastly over time in their ability to resolve structures. On the top left here, we have, let's see, do I have a mouse to, I think this works. Does this work? Oop, there we go. Here we go. So here we have a scattered wave image. This is basically a receiver function on steroid image. It's looking at scatterers. And where you see a transition from red to blue, you have a discontinuity. And what we're able to see is the basaltic oceanic crust coming in, eclogitizing, and disappearing into a seismic velocity structure that's similar to the mantle around it. Similarly, here, a tomography image of a subduction zone where we have earthquake locations and velocity structures that allow us to really link how water is released and how that relates to seismicity. But in the end, a lot of these things end up being fairly cartoonish. This is, I think, my favorite XKCD cartoon of late. And we'd like to do better. And we've known for a long time, and for anybody who's ever done photography, we know that more data, more pixels, more better when it comes to imaging. And so this is a study from 2015. It's a purely synthetic study, but they sort of said if we wanted to be able to recover a very simple seismology structure here, and we look at scattering alone, and we go from 1 kilometer, 5 kilometer, 10 kilometer, 20 kilometer station spacing with a reasonable amount of noise, you can see the degradation in the imaging that you have. In addition to that, while your resolution at shallow depths depends on how close your stations are together, your ability to see deep structures depends on how big the aperture of your array. So more and more, if we want to see deep structures at good resolution all the way down, what we need is a combination of really big areas covered with really fine station spacing. And of course, that's the double whammy. That means we need to install a lot more seismometers. So why not? Why aren't we out there? Come on, get with the program. Let's install more stations. Here we have our tens of thousands of stations, but why not an order of magnitude more? And quite frankly, the answer is simply that field seismology is hard. This is something that Rick Carlson understood in his bones and in his back. And if his barbed wire experience was similar to mine in the scar tissue on his arms. So I wanted to, since this is a symposium to what Rick has learned, take you with a quick tour of what all goes into a seismic deployment. First off, you have to get the equipment that you need. In the country, in the US, that's usually less trivial, though you still have to store it somewhere and schlep it around. But if you're international, often it's really hard to find something as simple as a plastic box to put your recording equipment in. And so in this case, on this bottom right photo here, this is from a colleague of mine, in Chile, they had a hard time finding a plastic box, so they bought plastic doll houses to serve as their battery and data logger holders. And they worked. But can you imagine walking out of a store with 50 plastic doll houses and trying to explain that you're a scientist? Yeah, I know, right? Yeah, I'm sure NSF had fun with that. So, and you can spend real time. So for example, the Carlson frame, as wonderful as it is, it turns out that in Peru, you can't get metal fence posts. This was really frustrating because the Carlson frame was so awesome, as we've heard, but it doesn't work without metal fence posts. So we had to figure something else out. Once you've bought all this equipment, you have to get it to whatever sites you have. There's a picture that I took of, or that we have of Maureen with yet another flat tire. How many did you shred over the years? It was pretty solid. The roads themselves are precarious, and depending on where you are, you can't always get vehicles with significant ground clearance, so you can get stuck. The roads themselves are not always set. This particular picture, we had to turn around and couldn't do field work that day. This was at the crest of the Andes east of Lima, and there was a head-on collision between a passenger bus and a gasoline tanker at a hairpin turn that, of course, somebody was passing someone else, and so, And then, you know, when you get there, really, you know, with the barrels and the concrete and all of this giant equipment, you've got maybe 1 or 2 stations worth of stuff in there, which means that for each station you have out there, you now have to go back on that road to your depot to pick up more equipment. So there's lots of driving, lots of exciting driving. Then you get to dig a hole, a big hole. I have a PhD in digging holes. You have to put cement in there. It means you have to get the cement there. You have to know how to mix sand and the cement mix just right so that it actually sets. You also have to have water, and depending on where you are, you're often bringing it with you. You then have to get the seismometer in the hole and orient it, and God bless the STS-2. It is a lovely piece of equipment, but Streckhausen, in his infinite wisdom, decided to make the orienting rod point east just because things are otherwise too easy, and it's at the bottom of a barrel, so there's lots of pictures of all of us leaning into holes in the ground. You then have to wire everything up, and you have to make sure that even after all of that labor, and usually you've got some gut plague or you're at high altitude, so you're a little woozy, you've got to make sure you wire it up properly so that you don't come back and find out you didn't quite get that right, and then package it up and come back 6 months later to find out what you did wrong. So let's see, some of my favorite field photos. Here's you see this guy right there? That is a black widow spider showing her belly at her finest. This is what you don't want to find when you walk up to a seismic station, your solar panel frame with no solar panel on it. This was a box that looked like that. At some point, somebody looks like they filled it with gasoline and set it on fire. A sensor vault filled with water, or even worse, if your battery and instrumentation get soaked together in water, this is what happens to a metal plug over the course of 6 months with a deep cycle battery and water. After 2 years, you have to pack it all up, and the big trick there is that internationally, if you get stuck importing a cute little spider somewhere and all of this equipment, you're in big, big trouble. And they have the ability to actually deny you the ability to ever ship internationally again. There's this 3 strikes policy, and it is no joke. So we spend a lot of time scrubbing seismic equipment. So there's a lot new on the horizon. Seismic technology has come a long way, and especially in the last decade or so. The newest sensors, they are waterproof and dirtproof. They're smaller. They're lighter. They are much lower power. So instead of like a 2.5 watt system, we're down to about a 1/2 watt system for a full broadband station. And they're a lot less delicate, which means that they're much less likely to break in shipping. And that alone means no more barrels, no more concrete. That reduction in volume means a lot less driving and a lot less chance of data loss with the low power. But here at Carnegie, we took it one step further, and we wanted to make sure that we got those deployments right, that we could get them in the ground quickly, and that we could really capitalize on this new equipment. And so with Rick's support, Diana and I have been working on developing the Quick Deploy box, where it's a Pelican case. It's 100% waterproof. There are bulkhead fittings. It's pre-wired. So there's no wiring in the field. Everything is set up before you go. You get there. It is designed to be plug and play, square peg, round hole, so that no matter how brain dead you're feeling at the end of a day of field work, you can't wire it up wrong. We even have captive screws, so you're not going to drop a bolt into the deep grass or mud and have to go hunting for it for half an hour. Not that that's ever happened to me. It's small enough to be checked on an airplane, so if you can't drive to a location, as is going to be the case for me in some cases, you can fly it. And it's inconspicuous, which means the odds of it disappearing over the course of the deployment are much, much reduced. So we've tested this a lot. Diana showed some pictures of these quick deploy boxes out on volcanoes. We also all did a pandemic at-home test deployment with the broadbands, and so I was able to put this full broadband station into my backyard at the height of a DC summer in the middle of the day in less than 2 hours by myself. And if you consider that in the HLP, it took a 4-man team pretty much a full day to get a station in the ground, that is a huge improvement. And really significantly ups the potential for making these deployments much bigger and dramatically increasing our resolution. And for this, Rick, I really have to thank you, because it has been a few years collecting through, I think, brute will, the funds to be able to put this together, to buy this new novel technology, and to be able to build these quick deploy boxes. We've had multiple iterations. It has been a sustained effort. And we now have 12 quick deploy boxes for all volcano work and rapid response, and 25 full broadbands. So I wanted to tell you a little bit about where these full broadbands are headed. I have an upcoming project looking at Columbia. The tectonics here, particularly complicated, and as you might not be too surprised to hear, it has been a while since anybody has done the types of deployments that we've done elsewhere in Columbia. Now, they have a fantastic network in country, but it's pretty broadly spaced. The interesting thing here is that you have two plates subducting. You have the Caribbean plate subducting, possibly, but very, very slowly. Let's see, where's my mouse? Mouse just does not. Oh, here we go. So these are vectors showing the convergence rates. Relative lengths are relative to convergence velocities. So you have the Nazca plate subducting from the west and the Caribbean plate subducting from the north. And you have two dipping planes of earthquakes, what we call Wadati-Benioff zones, defining where these slabs are subducting. And you'll notice that this northern section here, except for this northernmost part, is hundreds and hundreds of kilometers from the coast. And as somebody I think referred to me as, what, Dr. Flat Slab? This had my attention. Flat slabs are great because they shut off the volcanoes, so I've always focused on places where we don't have things erupting on us. But in this case, there's an abrupt offset and then normal subduction complete with a modern arc. And so efforts to image these slabs have produced really heterogeneous models of where the different slabs are, where they're interacting with each other, even how many slabs there are subducting across this region. We looked at some arc volcanic histories and came up with a new model whereby we think that basically there used to be a much bigger flat slab and that the southern flank of that failed about 3 million years ago. And if that's the case, what we're looking at is a modern analog of what happened 35 million years ago in the western United States when that big poof of volcanism that Maureen showed in that video came through in response to the Farallon flat slab falling off. This, if we're right, this happened very recently in Columbia, and that gives us an unprecedented look at what those processes were back then. And so to do that, we have the Musica project, and this is me trying to be Rick Carlson, putting together a large multidisciplinary international project with seismology, geochemistry, geochronology, structural geology, basin analysis, thermochronology, geodynamics, and also a substantial education and outreach component with the Carnegie Academy for Science Education. In total, what we're looking at here is 75 seismometers. That's actually less, substantially less than what we had in the high lava plains. But that's in part because at the time I didn't know that COVID was going to happen. We were scheduled to deploy in summer of 2020. And 75 stations of the old type of equipment was more than enough. What's turned out to have happened is that in the interim, Pascal has recognized the value of the new technologies that we've long since adopted and that Rick has long since supported, and has now bought 100 of these stations to be able to lend out to us. Now they are, I think they've ordered them, so they are coming online this summer. So we will be deploying the 25 Carnegie quick deploy boxes this summer, which quite frankly, I probably wouldn't be able to do anything this summer because of NSF rules having to do with State Department travel advisories. So the fact that I can go in the field at all is because we have this new equipment. And then we're going to, in January, go out with the 50 sets of equipment from Pascal, but we're buying the quick deploy box enclosures that we developed here to couple with them. And while buying those is not an insignificant expense, the money that I'm saving in deployment costs pretty much covers it, right? And those boxes don't go bad. So we'll be actually returning about 40 of them to the Pascal Instrument Center for other scientists to use and work with moving forward. And so that's a legacy not just to us here at Carnegie, but to the entire seismology community. Once again, Carnegie helping to lead the way. And, you know, we have a geochemist to thank for it. So Rick, I wanted to thank you, as so many have before, for your vision, for supporting seismology, for seeing what we can offer in terms of the end of the evolutionary continuum for planets. And I wish you really the best in retirement. It is well-deserved, but we are going to miss you. So, thank you.
Thanks so much, Lara. Exciting to see where these QDBs are going to be heading next. I think if anyone has any questions in the audience, we can
also just go to break and
there's
have
also
coffee and talk to me there.
a coffee break, so that can be a time for discussion. Oh, one comment from the Zoom quickly. You should put Vaseline on the exposed electrical connections in your field boxes, trick of sailors, to prevent oxidation.
Good to know. All right.
From Dominique.
Okay, thank you.
Thank you.
You're good. I don't hear anything from Al.
Okay. Oh, right. Is it still on? Yes, it is. Still on, yeah. Good. Yeah. I think it, yeah. It's all part of the plan.
Hello, everyone. My name is Jens Barosch. I'm a postdoc at Carnegie, and I welcome you to the last session about the lithosphere. And our first speaker is Graham Pearson from the University of Alberta, and his topic is the craton concept, the root is the key.
Thank you. Well, like everybody else, it's an honor to be here to celebrate Rick's retirement. I'll just start by acknowledging the contributions to this work from two PhD students, Jiwei Zhang and Christy Kublik, and my faculty collaborators here that have contributed. But I thought I'd start by outlining a few Carlson characteristics, at least from my point of view. You've heard about a few already. And I mean, there's enough gray in my beard that I don't come from the generation where we had cell phones to take pictures of people. In fact, I'm terrible taking pictures of people. I've got a lot more pictures of fish than of people. If you want to see pictures of fish, I'll show you pictures of fish. But I've got one picture of Rick, which we will see shortly. So, I mean, this actually goes for many Carnegie people, that being unafraid to get your hands dirty. And so more than once, I've come into the mass spec lab, and Rick's been sat on the floor in a pool of oil with a rotary pump in bits, possibly more bits than you started with, but in bits, and he's trying to put it back together. But that characterizes the Carnegie ethos of just get stuck in. I mean, we've seen people digging holes in the ground and stuff like that already. He has an unfailing commitment to the truth, as all scientists should have, and you often find yourself, Rick's a co-author on your talk, and you give the talk, and it's all gone well. There are no questions, except from your co-author, who has a really good, annoying question, but he'll ask it. He seems to be under the delusion that the baseball players can throw a ball further than cricket players. So there's a witness in the audience to this event. So I think it started one beer hour where I think I probably lit the blue touch paper with Rick because I made a comment about the inability of Americans to catch a ball without a dustbin lid on their hand. And then the following Monday morning, I'm running a sample on the mass spec, and my boss turns up with a baseball and a referee, Bill Hart, and we find ourselves on the lawn in front having a throwing competition. Curious. It would be rude to say. Ask the judge. And then Rick really has an infectious enjoyment of science and doing science experiments. And so the one picture I have is him. He's in the clean lab, my memory's a bit foggy, and he's celebrating a particularly good blank on some distillation product. And there's someone else that seems to be equally infused about the good blank. The lighting wasn't very good in the clean lab in those days. I think that was what was going on there, wasn't it, Rick? I think that deep vision he's got seems to have got a bit blurred in the eyes there. So. Anyway, but more seriously, so this paper persuaded me to do a postdoc. I think I was going to go off and work in the mining industry or something. And then I saw this paper when I was a grad student at Leeds working with Peter Nixon, and I thought, wow, that's an opportunity. So that really was completely instrumental in getting me to do a postdoc. Working with 3 mentors here, I mean, how can you fail when you've got that sort of backup? Well spotted, correct. Yeah, you can't. That's the problem with showing things to geologists. They're trained in observational science. All right, so we'll talk about a bit of science. So there's a sort of three-course menu. One, how can we better define what cratons are? Because the mantle petrologists in particular are terrible about the way we talk about cratons, and I'd like to propose a way of clarifying that. We'll look at the early life of cratons, which hopefully give us a bit of insight into at least how some of them are made. And then we'll look at how cratons evolve with a curious example. You won't like my model, but I'm putting it up here for feedback. But it's a location close to Rick's heart. Okay, but we should start with the question, why study cratons, or why study the lithosphere? I mean, if we can't understand Earth's lithosphere, then we really haven't got much hope in understanding the lithosphere and other planets. So we need to understand Earth's lithosphere. Plate tectonic theory was really successful at working in the oceans, figuring out what's going on in the oceans. It's been a lot less successful figuring out what's going on in the continents, and the key to making progress there is to just look at continental lithosphere more. This is very topical. I mean, apart from the gases that we mine from the atmosphere, all 100% of the extractable minerals, including the critical metals that we're all going to be driving around in with cars with soon, are hosted in the lithosphere. That's a good reason for understanding the lithosphere. Cratons play an outsized role in that economic inventory. And then there's the whole relationship to, without understanding the whole lithosphere, in my view, you can't understand one of the bigger scientific questions of the time: how did Earth's crust evolve? So we'll start with this. It's a classic Joe Boyd image. Joe was another Carnegie mentor, very influential on me. And this is a typical Joe Boyd image drawn by hand. And it illustrates what people sort of defined as the craton at the time. And it illustrates this mantle root here with diamonds in it. And the inference is that the root is thicker beneath the craton, as defined in this image, which is the part below the Archean crust than it is in the Proterozoic crust. And that was the sort of state of the art at the time. But it turns out that that's not really true, and neither is the stable since the Archean. And so, you know, a little example of that would be this thing that we call the Kapval craton. Well, I'd like to refer to the central part of cratons. I'd like to start calling the Archean nuclei. It's not a new term, but we just need some consistency because the craton is bigger than the Archean. I think that's what I'll hope to persuade you of. And this illustrates, it's not my publication, it comes from Jacobs, but it illustrates the post-Archean history of the Kapval craton is very complex. They've not been stable since the Archean. In fact, what this map misses off is the world's largest igneous intrusion is smack in the middle of the craton. So we've got this history of accretion of additional terrains at 1.8 to 1.7 GA. That goes on. We've got the Umkondo large igneous event here at 1 GA. And then we amalgamate those nuclei into this composite Kalahari craton where you've got Archean nucleus, Paleoproterozoic and even Mesoproterozoic outer region, and then later deformation around the edges of that robust nucleus. Okay, so how's this all linked to the root? So this is a very transformative image, and which we've seen already. Thank you, David. We'll talk about this area shortly, but the curious thing to me always has been about this image, these things. I mean, we focus on, okay, so there's nice, cold, deep lithosphere beneath the cratonic core, but there's actually equally deep lithosphere off the nucleus. And that's a very common theme, and that's not just present in that image. This is a recent paper. I think they use your data in this and reprocess it, but it's the same story. And you can see, for some reason, they seem to have enhanced the coverage. I don't know how you do that, but they do. But there's more of this, if you just focus on the 200-kilometer region, there's more of this thick lithosphere outside of the cratonic nucleus. So that image that I first put up isn't quite right. And when you look at this on a global scale, this is an image that Andrew Schaefer created. It's kind of a bizarre session, this. We had a geophysicist explaining the fundamentals of rhenium osmium isotope geochronology. Thank you, because I don't need to do that. And now you've got a geochemist showing seismology. It's become clear I don't really understand.
Yeah. But so I mapped on here 43 of the extant Archean nuclei that I could find. And there, you might not be able to see them too easily, but they're the faint lines on here. And you can see that the deep lithosphere extends way beyond these Archean nuclei. And that's a key concept. Another idea is that if you go to Brazil and you go to the so-called Amazon craton, in the old definition, spot the Archean. I mean, you have to work hard. It's in here. It's the Carajás terrain, but but this belies somewhat. Sorry, it's there. It's the orange stuff, 3.0 to 2.5. That is a rather simplified view of it. There's a lot of younger stuff in there, and then you've got the kimberlites. All occur. They erupt in the Paleoproterozoic, including the famous superdeep Juina location. And so then, I know this is global tomography, sorry, but I couldn't find the high-resolution study. But it's quite obvious that there's deep lithosphere well outside what little Archean you can actually find there. So then craton stability, if craton stability is defined by the lithospheric mantle roots, because they're highly depleted, so they're buoyant, highly depleted, so they're viscous and therefore strong, and that leads to them preserving their identity for gigayear periods, then it just seems to make sense that I mean, the crustal geologists don't like this, but why not use the root in the definition of a craton? And you know, the visual reasons for this is rhenium-osmium geochronology, which our seismologists explained very well earlier. So we've got the ratio here, high degree melt, 0 rhenium-osmium ratio, and you read off the model age. And so I mapped out this is a compilation of mantle root ages beneath Archean nuclei. These are mantle root ages beneath cratonic regions that are really dominated by Proterozoic crust. And these are what I would call now modified cratons, for instance, the Sino-Korean or the North China craton. And you can see that Archean nuclei are underpinned by, in general, Archean roots with some more complex age spectra that we won't deal with right now. The Proterozoic crust is underpinned by, you can see some vestigial Archean root, but the mode in the data is in the Paleoproterozoic here. There's a big mode at 2Ga. And then these modified cratons, like the North China craton, we can't really distinguish the root, the lithosphere there, from modern oceanic crust. I put on here a really nice paper that Jesse described that he wrote about the first appearance of fully mature sediments from large drainage basins that suddenly appear when cratons first start to be made. I haven't got the time to get into that, but that's a really interesting avenue for exploration. And then we've got the rhenium depletion age versus composition, and really the point I want to make about this is that not only have you got very depleted compositions in the Archean, but those highly depleted compositions persist right through into the Paleoproterozoic, 1 or 2 in the Mesoproterozoic, and they kind of disappear here. There's a few really depleted compositions here. These are subduction zone residues, but by and large, there's this nice transition in the degree of depletion of the lithosphere. So ancient depleted mantle roots underpin Archean to Mesoproterozoic crust. They're not restricted to Archean nuclei. And so that then leads into a revised working craton definition that would go something like cratons are coherent blocks of Precambrian lithosphere, typically stable for time periods in excess of 1 billion years. There's some slop in that. There are certain cratons where there's a lot of reworking that's gone on to 700 MA. But owing to the protection, or their protection by deep 150 kilometer plus lithospheric keels. So the majority of Earth's Archean crust lies within these terrains and can be referred to as Archean nuclei, but the moniker craton is not extensive to the Archean. And I think a lot of crustal geologists know that, but it's not used in a systematic way, and I think it leads to a lot of confusion. Then we have these larger composite cratons, which may consist of several Archean nuclei surrounded by Paleoproterozoic to Mesoproterozoic crust, which an example would be the Kalahari craton, where we've already sort of looked at this, so I'll skip on. But here's the Zimbabwean portion, the Kapval portion, amalgamated into what you could call the Kalahari composite craton. And then there are these bigger entities. I'm going to skip that because it's the same thing, called supercratons. It's really a term that Paul Hofmann introduced for something like Laurentia. And the supercraton is an amalgamation of composite cratons into a much larger body. So this is data from the US array, I think. It's a Schaefer and Lebedev image of North America. And you can see that, so here are here's the geology map. The Archean provinces here, these Archean provinces, the ray, for instance, is peppered with Paleoproterozoic intrusions. But the point really I want to make is that the deep, strong lithosphere extends well into these Mesoproterozoic regions. Yeah, sorry, I think that's the S-wave image. So S-wave anomaly, and that's a 150-kilometer slice. So, I mean, if you get a major point out of this, is that deep 150-kilometer thick lithosphere exists beneath continental crust of widely varying age, not just Archean nuclei, right through to at least Mesoproterozoic. The Mesoproterozoic seems to be a really good cutoff where you stop getting 150-kilometer thick lithosphere. And Archean nuclei tend to be underpinned by Archean mantle lithosphere. Proterozoic domains tend to be underpinned by dominantly Proterozoic lithosphere. I'll show an example of that. Neoproterozoic and younger crustal basement tend to have lithospheric roots less than 150 kilometers. Okay, so let's move on to, defined at least to my satisfaction, the idea of what a craton might be. We'll look at the early history of cratons. And so that's been dominated by diamond science for a good reason. So here really is the first concrete evidence that these roots were A, old, and B, enriched. I'm sorry, I had to show a neodymium isotope slide here. Really the key bit is the Mesoarchean old enriched lithosphere here from Steve Richardson, who sat in the audience. Steve was also involved with the other Steve here in producing this age for Panda in the Northwest Territories, which is Meso to Paleoarchean in age. But these are constraints from diamonds that were erupted in the Mesozoic. So although they're very good at giving you a lot of information, they're limited in that they're not telling you about physical mantle conditions in the Archean, or they don't hold as much information as Archean diamonds that were extracted in the Archean out of the mantle. And that's where I want to go next. So with the remains of a grant that I had where there's enough in it to go on a speculative trip or maybe analyze a few more kimberlites, I decided to roll the dice. And so with Jesse Reimick and a postdoc, Adrian Vezenet, we went up here onto the Arctic coast where there was an unsubstantiated report of one little diamond in a quartz pebble conglomerate, an Archean quartz pebble conglomerate, but they lost the diamond. That happens more frequently than you might think, actually. If you drop a diamond, they bounce, and they go a long way because they're very hard. Anyway, so here we are on the Arctic coast, and we zoom in. This is the slave craton here, so, oops. Here we are, that's the slave, that's the slave, in new terminology, Archean nucleus. The craton is the larger body. And it's pretty complex geology. Yeah, let's not get into that. And here's a rock. There's the quartz pebble conglomerate, nice looking rock. Turns out this is a really good gold prospect, and these basal conglomerates, they're basically the erosion products of Archean basement complexes. And it turns out they're great prospects for gold. All right, gold not an especially useful mineral, but they're also good prospects for detrital rare earth minerals, which is something I didn't know. And I'm sure that many of them have diamonds. The problem is the diamonds are very small. They're not easy to find. Now, so we collected more than 15 kilos, but in one 15-kilo aliquot, we're getting pretty good at finding little diamonds. These diamonds are the size of the inclusions that we usually study, 0.1 millimeters here. We found 3 diamonds in The people at SRC that we work with, they actually find the diamonds. They're the world leaders in recovering microdiamonds from rocks. These are cathodoluminescence images. And so that was worth the trip on its own. But these tell us a lot, because keep in mind, these are diamonds that were taken out of the mantle in the Archean. So they preserve a lot of information if you can find solid inclusions in them of what the conditions were like in the Archean. Now, of course, they're the size of normal inclusions themselves, so finding inclusions is a bit tough. And so you have to do that by X-ray techniques. First, we wanted to establish the age of the potential age of the diamonds, and so we use uranium lead. I'm not going to go into the details. We get a maximum age of deposition of this sediment of 2.83, so Mesoarchean deposition age for this sediment. And then we sent the diamonds to Fabrizio Nestola in the Department of Geosciences at Padova, and Fabri has one of the world's most sensitive non-synchrotron mounted X-ray systems, and he found, amazingly, a tiny little olivine inclusion in there. This isn't it. It's too small to see, actually. But the beauty is it's so small that it's not exerted too much stress on the host diamond, so there's no cracking in it. And that means that we can use a technique that's been around for a long time, but that Fabrizio's lab have really developed, called elastic geobarometry, to estimate what the pressure conditions were like when that inclusion was trapped in the diamond in the Archean. Oh, gee. This is why Rick thinks that I have trouble operating a mass spectrometer. Not unjustly. So the idea is that you've got this diamond with a trapped inclusion, and we want to get back to this pressure and temperature of crystallization, or trapping at any rate. The inclusion's under pressure, and so the diamond gets taken from the deep mantle, it gets erupted onto the surface, there's decompression and cooling, except the diamond's not very good at decompressing. It has the highest bulk modulus of any mineral, 444 GPa, is that right? Very high. So this host isn't going to expand, but the inclusion wants to expand like mad, and that leads to a residual strain or pressure, and you can estimate that, especially if, as they did in Padua, so you come up, or they have come up with full nonlinear elastic theory for both the host and inclusion, olivine and the diamond in this case, carefully validated equations of state, make corrections for non-spherical inclusions. And there's some nice software to go with this that you can download. And so in this case, we made an estimate of the residual pressure using X-ray diffraction and lattice parameters. And that shows that this tiny olivine has a residual pressure of somewhere between 1 and 1.5 GPa. Using that residual pressure and the elastic properties of the diamond, you can then get a really surprisingly good estimate of the pressure of entrapment of that inclusion, 5.9 to 6.3 GPa. That's as good as you can do with element exchange geobarometry, which is surprisingly good. We can estimate the temperature, or at least the residence temperature of these diamonds from the way that nitrogen aggregates in the diamonds. And so when we do that, there's two of the diamonds didn't have any nitrogen, which is a curiosity in itself. The one that did has average nitrogen aggregation, well, concentration of 1300 ppm, of which 4% is in what's known as the B-aggregated form, where single nitrogen atoms aggregate to pairs, and then eventually to 4 nitrogen atoms and a vacancy. And that's a temperature time control process. It turns out it's a much better thermometer than it is a chronometer. And so that temperature estimate, if you put in a wide range of residence times, it's again, surprisingly tight at between 1160 and maybe 1170. Okay, there could be a little bit more error on that, but actually not that much. So that puts you on the coldest geotherms that are extant in cratons today. These are geotherms from mantle xenoliths erupted in the Mesozoic. This is a point in PT space preserved from the Archean. That gets really interesting. I mean, how do you do that in a hot early Earth? So it implies a geotherm that's as cool as any present-day craton. And if you keep in mind what's happened here, we've got to make the diamonds, we've got to erupt them to the surface, we've got to form a sedimentary basin, and then we've got to put the diamonds in the basin by erosion. And that all has to happen quite quickly. How do we constrain the time on that? I'm going to go to that. No, I'm not. I'm going to go to this. Okay, so we've got these diamonds on a very cool geotherm. So how do you get that thermal situation in the early Earth? In the context of, you've also got to be, that's in the time frame that you're actually supposed to be making the craton. So if you just take the two simple end-member scenarios that the lithosphere forms by vertical accretion of plume residues, then, and this is a thermal model done by my student Christy, so here's our relaxed geotherm in the black dots here. Here's the PT point we've got. And so a plume, the problem in many circumstances with making thick lithosphere by plumes is the cooling time scale. And so after 500 million years, you're still way above this relaxed geotherm that, or even if it's not relaxed, you're above this point in PT space that we've determined from the diamond. Here's a thermal evolution model that you get from slab stacking. And it's actually very easy to be in this PT space for some time before the thing sort of warms up and eventually equilibrates to a relaxed geotherm. So this seems to indicate, at least in this case, a model for craton generation by slab stacking. I mean, it's just very difficult to get that very cool geotherm in the Archean, in the Mesoarchean. The timing on that also comes from, we also were working on, this beautiful green color. This is a fuchsitic quartzite, and the green color comes from weathering of these chromium minerals, chromites, to give the green color. What we're really interested in is that the chromium traps a lot of osmium. You can date the chromites. The chromites, it turns out, come from komatiites. You're just going to have to take my word for that because I don't have the time to get into it. And so these quartzites predate by about 1 to 200 million years this initiation of this sedimentary basin. You can't really make magmas like this unless you have some sort of thinning lightly associated with a mantle plume. So you've got this extreme architectural evolution of the lithosphere where you've got thin lithosphere to make the komatiite. There's gold forming possibly at the same time. There's plenty of gold in these conglomerates. And then you've got to then stack slabs to make a cold geotherm, erupt the kimberlite, erode the diamonds into this basin that's developing. You've got your gold, your chromite, and goodness knows what's happening in that time scale. So extreme evolution of lithospheric architecture on a really quite small time scale there in the early stages of craton formation. That's in press at the moment. My postdoc Suzette Zimmerman wrote up all that. It's in press in EPSL. Okay, how am I doing for time? Oh, okay. So then the last part of the talk, I'm going to talk then about modifying cratons in their later life. And we're going to visit the Bushveld intrusion, which has already been alluded to, because it's an enigma. I mean, nobody has a good explanation. And I guarantee you about what I'm about to say, there'll be a number of people in the audience that will completely disagree with most of it, because that's the nature of the Bushveld intrusion. But it's located, so here's our Archean nucleus. Bushveld intrusion is in the middle of this great big scar that was one of the most important results identified by the CATVAL project, that you can see this effect on the lithosphere. It had a profound effect on the lithospheric root. So the Bushveld intrusion ought to be more broadly known as the Bushveld-Malopo Farms complex because it extends into Botswana over here in the west. It erupts kind of along this Tharbazimbi-Murchison lineament here. And it's 250,000 cubic kilometers of magma that erupted into an intrusion very quickly within less than 5 million years. It started, crystallized, and it stopped. That's not easy to do. So it turns out that there's a kimberlite that punches through this area called the Premier Kimberlite. It's now called the Cullinan Mine after the Cullinan diamond, after Mr. Cullinan who owned the Cullinan Mine. And we have a very nice suite of mantle xenoliths from that location. And you know, geologists are inherently splitters, so we divide our xenoliths into different groups. So we've got 3 groups that we've identified on the basis of petrology and major element chemistry here, referenced against typical CATVAL mantle peridotite. And I'm not going to go through all of this slide, except to say that, so there's a group 1 part of these xenoliths that are very depleted, aluminium contents, which is a a measure of the amount of melt you've taken out of these xenoliths, as is the olivine forsterite content. High olivine forsterite, low aluminium means lots of melt taken out. And so group 1, very refractory. Group 2, slightly less refractory, but still, up there on the scale, melt residues. Group 3, the deformed group, I'm not going to talk about too much, but are actually extremely interesting. When you look at the platinum group element patterns of both group 1 and group 2, which I should have plotted leaving the blue group off for the time being, but all these platinum group element patterns, when you take melt out of a peridotite, not much happens to, if you have a reference line on here for, say, abyssal peridotites, which most of you think of as respectable melt residues, but taking out more does very little to the platinum group element pattern of a peridotite. To get these are the incompatible PGs. To get these patterns, and actually especially to get these enrichments in osmium, you've got to take out large amounts of melt. The point I want to really make here is that both group 1 and group 2 xenoliths are characteristic of melt residues. So the question is, can we see any impact on the lithospheric column under here by the Bushveld intrusion? I mean, it would be astounding if the answer to that was no, obviously. And so Rick started this work, so there's a lot of Rick's data in here, and there's a whole lot of new data. So we've got osmium ages for, does it say? I think, yeah, 46 mantle xenoliths now in here. And you can see that the age pattern, these are rhenium depletion ages, are dominated by 2Ga. What's the age of the Bushveld complex? 2Ga. There's a vestigial peak here that is related to, this dashed line here is the ancestral Kapval craton background signature in the Neo to getting into the Mesoarchean. And we've got 1 or 2 ages that are even older here. So we can see this impact of what was, or the signature of what was there, and then we can see the impact of the Bushveld. And our view is that these are residues created by the Bushveld intrusion. I mean, how do you generate 250,000 cubic kilometers of melt without having melt residues? So, so if you're into mantle plumes, then you'd say, so, all right, so those are plume residues that have just filled the gap, and that's what we thought the answer was going to be, until you measure the rare earths, and you can use rare earths, ytterbium, a heavy rare earth with aluminium, against calibrations from melt depletion experiments, actually some of Mike Walter's experiments for the aluminium and some other experiments for the heavy rare earths. And the trend here is a low pressure melt environment. Now we have a suite of peridotites from the slave craton that we're pretty sure are high pressure melt residues, and they have, so in high pressure melting you have garnet stable, it keeps the ytterbium, and this is a group of peridotites that has that signature. It's very difficult to make signatures like this from high pressure melting, and that gives you a bit of a problem. You've got this giant magma system, and so here's where we get into the model, which is speculative, but there's lots in this model. The plume thing, I mean, the plume might be completely wrong for the Bushveld intrusion, and maybe a better model is either Columbia River lip, and I started thinking about some of Rick's work in the high lava plains and what happens when you have slab drawback here. So here we've got a situation, this is 2.1 to 2Ga, where you've got, we'll just throw a plume in there anyway because everybody does. And so you've got some melt going on here. You've got a ridge here pushing a subduction zone out here. This is the Cais Aqua Magondi belt that's being subducted underneath the margin there. And then either you have slab rollback here, which pulls this plume over here because you make this massive Bushveld complex, and then it just stops. So how do you shut that off? And something that Laura said in her presentation about, well, all right, maybe not slab rollback, but do you have a flat slab under there that just cuts off? I mean, you're making this vast amount of magma, and the lights go off. So maybe, maybe rather than rollback, you have a flat slab. I mean, there's some dynamical problems with this model. I wanted to present it just to get feedback, because we don't know what's going on. We're trying to understand how you can do this. We've got low pressure residues that are not, so I'm not arguing that you cannot possibly have a plume involved, but the healed lithosphere doesn't have the signature of the plume. So you've got to put some residual mantle into there from somewhere else. It just struck me that shutting off that magnetism quickly, you might do from a flat slab, and then you need some jiggery-pokery to somehow get this stuff into here. And I'm trying to work with some dynamic modelers to give us a little bit of realism as to whether this might work. If you've got a better solution, please tell me. Anyway, but it's a real enigma. You know, if we can't explain the origin of the biggest igneous intrusion on Earth, again, how are we going to do this with other planets? We need to understand how this happened. And the curious thing is the scar that it left in the lithosphere is illustrated quite nicely by a paper Steve wrote, where if you map out the eclogitic inclusions, in other words, in diamonds, those inclusions that formed from slab-like things, this zone here is really where most of the eclogitic inclusions in the Capval craton in diamonds occur. With one exception, Jagersfontein, and those of you that were paying attention, Roberta, will clearly remember that Jagersfontein on my age plot, I forgot to point it out just to test you out, was the only other locality that's got a 2GA peak here. Now, I can't explain the geometry of that, but it's an interesting coincidence. All right, so with the 1 minute I've got left, I was asked to say something about the future by Steve. I better not upset him, so I'll be brief. I mean, I really do think that if we were going to understand the early evolution of cratons, then finding more of these diamonds that were taken out of the mantle in the Archean is really going to be very helpful because it tells us a lot about the lithospheric architecture that was extant in the Archean. And then I'm working with a lot of dynamic modelers, Claire Curry at our institution. We co-share students where we're trying to understand the dynamic modeling of craton formation, and in particular the topographic evolution of cratons, where we're looking at how do you form these intracratonic basins, which are often world-class mineral deposits. I haven't got time to get into the models, but you know, here's a typical dynamic model, Christy Kublik's thesis, where we're compressing a craton, we're thickening it, and then we're varying the erosion rate and sedimentation rate. When you don't have any erosion in this model, you generate giant mountains. When you've got a little bit of erosion, those mountains quickly disappear and you start depositing basins, and we're trying to calculate basin fill trajectories. Anyway, that's the future, but that leaves me just to put up a nice picture of the mantle. This is in northern British Columbia. Rick wouldn't like living in Canada, he's told me, because it's a bit too cold for him, but and I can sympathize with that. Well, I mean, we invited you in March and it was chilly. Indeed, so that's why you need to go to these places in the summer. That's a nice piece of Earth's mantle in the mountains. Anyway, happy retirement, Rick. Thanks. Yep. Yeah, no, I don't have to answer any awkward questions about that bush film.
Okay, we are moving on to the talk by Albrecht Hofmann from the Max Planck Institute for Chemistry. And the topic is uranium in Earth's early core. Are you there?
Yep. Can you hear me? Okay. Whoops.
We are switching.
Yeah.
Can you share your slides?
That's what I'm trying to do, but I have just a minute. No. Gotta go back. Oh, shoot. I gotta go back. I can't get back.
We can't hear you. Can you share your slides and unmute your microphone?
I'm trying.
So apparently he can be heard in there and not in here, but
yeah.
I hope we'll figure it out.
Yeah, something happened just now. Shoot.
Hi, Al, can you speak up there?
All right.
Just say something for a test. Yeah, Al, we can hear you on Zoom, but we can't hear you in the auditorium.
Yeah, the screen just flipped on me, so I just have this tiny image and I can't get back to where I have any control over anything.
Do you have a second monitor set up?
Yeah, maybe I'm gonna try and sign in again.
If you stop sharing, actually, hang on a sec. I'll stop you sharing, and then you can.
I
Try
can't,
To share
okay, I can't stop sharing. I have no control at all right now.
I can do that for you.
Okay.
Okay. Would you like to share your screen again?
Oh, wait a minute. All right, now, but let me just make sure that I have what I need.
Perhaps you'd like to do the Q&A while we sort this out. Yeah, sure. I'll need this though.
Okay, maybe that'll be better.
Actually, I guess that's not fair on the Zoom participants.
That's
Sorry. Grab another coffee, everyone.
now the shares. Okay, share screen. It's just not doing it. I don't understand. Wait a minute, hang on. You see something now?
Yeah, we can hear you and we see your screen. Can you share the slides? Perfect.
Okay, that's the start. Oh dear. Okay. So I have an echo that repeats what I say. I don't know what's causing that. But all right. So I want to talk about uranium in the Earth's core early on. I don't really know anything about the core, which is one reason why it fascinates me. And I think because it provides the only possible solution to something that people call the lead paradox. And it's been my latest hobby. So this is a long-standing, unresolved so-called paradox, or there are actually two of them, that on the old Earth, when you look at lead isotopes in the Earth, they require a low uranium-lead ratio for old rocks, but a high uranium-lead ratio for young rocks, which is strange. And so as early as 1975, Stacy and Kramers noticed this and proposed a model whereby the Earth magically changed uranium-lead ratios 3.7 billion years ago. Of course, the Earth can't just change its uranium-lead ratio. What they also noticed was that at the same time, the thorium-uranium ratio required to explain the lead-208 and 206 ratios changed from something that we now know is superchondritic, namely a thorium-uranium ratio greater than 4, to, for younger rocks, to something that is more like actually chondritic. So there's been a literature addressing the lead paradox. Here's an illustration of just for the lead 207, 206 that shows the effect of changing uranium lead ratio. So old rocks conform to a constant uranium-lead ratio that's actually uranium-238 to lead-204 of about, this one is 8.3. But young rocks don't fit that line. They require a higher uranium-lead ratio. And that's been changed from 8.3 to 8.7. That doesn't look like a lot. The reason for that is that we have changed the age of the Earth from 4.5 billion years, from 4.57 billion years to 4.50. And I can't go into why we are thinking that this is a better age for actually the uranium-lead system of the Earth, but it probably was more or less set by the giant impact, and we heard about that yesterday. So 4.5 billion years ago is probably not a bad estimate for that. But so everyone has been worried about that change and what might explain it, and they called it the lead paradox. So they searched for hiding places for unradiogenic lead in the core, in the deep mantle, or in the lower crust. And at least once a year, I get a paper for review that proposes a new solution for the lead paradox. And they're all addressed to putting lead somewhere. It's all about lead because it's called a lead paradox. So sequestering lead would increase the uranium-lead ratio, taking some lead out, and it would change the growth curve for the lead 207, 204 versus 206, 204 ratio. But none of these solutions involving moving lead around address the so-called kappa problem, kappa paradox, which actually requires a change in the thorium-uranium ratio during the Earth evolution. And that, in my view, is actually the more serious problem because it cannot be simply resolved by changing the age of the giant impact from 4.57 to 4.50 or 4.45 or something like that. This thorium-uranium ratio is actually very robust, and it doesn't depend on the exact timing of the giant impact of the formation of the Earth. And here you see an illustration of that with a constant superchondritic ratio of thorium-uranium of 4.1. They fit the old data extremely well, but they don't fit the young data at all. So the younger rocks here, starting about 2 billion years ago, these require a ratio of thorium-uranium of about 3.8, which happens to be the chondritic ratio. So people didn't used to worry about that because they didn't know what the chondritic ratio was. So chondritic ratio of 4.1, 4.2 didn't bother anybody. But now we actually know, we have good data that shows that the chondritic ratio is very close to 3.8. Another way of posing this is to translate that, actually calculate a time-integrated thorium-uranium ratio from these lead isotopes. And there's the equation, and I won't go into this, that shows how this time-integrated thorium-uranium ratio, time-integrated means over the whole history of the Earth. For the old rocks, here's 4 billion years, they are around between 4 and 4.2. And then the younger rocks, they decrease systematically toward chondritic values. This just happens to be a curve I put through that has no particular meaning. It's just some kind of an arbitrary fit. But here you see some young rocks, there's some sediments, and there are some mid-ocean ridge basalts and young rocks on the whole. If you average what we know about the young Earth, the chondritic thorium-uranium ratio is okay. But none of the old rocks fit the chondritic uranium-lead ratio. And that problem is completely unresolved, and it cannot be addressed by any of the conventional solutions to the so-called lead paradox. So I'm going to explore two possible solutions to these problems. Namely, one is that there was some deep mantle fractionation of the thorium-uranium ratio. And there is one mineral in the lower mantle that might do that, and that is the calcium perovskite phase. And calcium perovskite phase has a high partition coefficient for both thorium and uranium, And if you have a solidifying magma ocean where the residual liquid is actually denser than the solid residue, which is actually likely in the lowermost mantle, we don't know this for sure, but it's certainly a strong possibility, then you might create a residual mantle with a changed or high thorium-uranium ratio. And this would then potentially explain the high thorium-uranium ratio of that early Earth. And later on, this reservoir got all mixed up. And so that effect disappeared. That is one hypothesis. The other hypothesis I'm going to explore is a sequestration of temporary sequestration of uranium in the core. So to go back to the first one, to the calcium perovskite version, let's just look at that for a minute. So here's some partitioning using experimental partition coefficients by Hirose and others, and with a pyrrolite composition. Then you can see that the uranium lead ratio of such a residue as the melt fraction changes goes up. So this is what we're looking for. But this is the thorium uranium ratio increases slightly, which might be enough. But that same fractionation also increases the uranium lead ratio, which is the exact opposite of what we need in order to explain the behavior of the overall lead system. Because what we need early on is a high thorium uranium ratio, but a low uranium lead ratio. But what this effect, the calcium perovskite effect, namely any kind of mantle process likely that could do this, causes an increase of both uranium lead and thorium uranium. So we can actually rule this out. So this mechanism does not work. The other possibility, and is in fact the only one that I can think of, is to sequester uranium in the early core, sequestration in the early core. But we then must release that uranium later on. So we're fortunate, just in the last few years, there's been quite a bit of high pressure experimental work that was done on this problem. One paper by Chidester, another one by Blanchard, Badreau, and others that show that at very high temperatures, the solubility of uranium in the core can go up to actually several ppm. Here there's 4 ppm, 6, 8 ppm. If you're reaching temperatures, a core temperature of as high as 5,000 degrees. So some people are uncomfortable with such a high early core temperature, but in fact, we don't really know what initially, it might have been 4,000, it might have been 5,000. So the idea is very simple. Initially, you have a mantle, which had, in this case here, 4.5 ppb of uranium. I should have said ppb, not ppm. That reduces the uranium content of the mantle from about 20 ppb to roughly 18. So that lowers the uranium in the mantle and gives you that that high thorium uranium ratio. And then after cooling the Earth and core cooling, that uranium is released because it's no longer, the core can no longer hold this uranium. And so the mantle then goes up to the chondritic-like value of about 20 ppm, and the effect gradually disappears. And one can model this somewhat arbitrarily. Here's some kind of an experimental growth curve. Here's the uranium lead ratio, how that would go with time. And here's the thorium uranium ratio, how that would go in response to that. And if you then model the lead isotopes from that, you can get quite sensible. This is now actually the model curve of the sulfide, lead sulfide data let's go back here. From these very high thorium uranium ratio to lower ones and close to chondritic value. Remember that these data here are actually for the time integrated. So the actual thorium uranium ratio at the present time is going to be lower than that because the time integrated ratio contains the memory over the whole history of the Earth. So that's basically, and the Stacy and Kramer's lead evolution curve can now fit with a single growth curve that fits all the data quite nicely with this increasing uranium lead ratio like that. And so that's basically it. That's my story. I have to go on jump in my car in a few minutes because it's my wife's birthday. And I'm just about at the time limit now for myself. I don't care about the symposium so much. Sorry, but here we go. My conclusion is in fact no lead paradox at all. Uranium does it all. The early incorporation and subsequent release of uranium fully explains the isotopic evolution of lead in the silicate Earth. And with that, I want to welcome Rick to the club of the Emeriti. Shall he have a long, happy life as an emeritus. And cheers from Germany.
Thank you very much. Are there any quick questions?
Al, are you still there?
Yeah, I'm still there.
Two things. One is give Julie my happy birthday wishes. But the other one is what are the problems you have with Bill White's model that has uranium preferentially recycling starting at 2 GA with the rise of oxygen because of the increased solubility of uranium in an oxidized Earth surface?
That's an explanation. I'm sorry. That is an explanation that is addressed to the low thorium uranium ratio of the Orb reservoir. I didn't talk about that, but that's sort of a detail in this game of things.
Okay.
That's quite true. It's actually Tim Elliott's model for explaining what he called the second lead paradox. But it doesn't explain the whole Earth evolution because the effect starts much earlier, whereas the difference between the Morb reservoir and the continental crust age requires essentially moving oxidized uranium from the crust into the mantle. So that's a second order problem here.
A quick question here, Dominique. How strong are the constraints that uranium is fractionated into the core and not thorium, as that's been checked?
Yes. The experimental data by all groups show that the solubility of uranium is substantially greater than for thorium. And the experiment came to the conclusion they were unhappy with their results because they didn't get enough uranium into the core to get much of a heat source in the core. They didn't worry about the lead paradox, okay, but I worry about the paradox. So, but the thorium is not a problem.
Any more questions for Albrecht? If not, then thank you very much for the talk and happy birthday to your wife.
Thank you. I'm off, right? Okay. I'm on the minute. Bye-bye.
Bye. So before we move on to the next talk, we should have the quick question session for the first talk, if Graham is here. Okay. Questions for our first speaker?
So, Graham, the proportion of eclogite in the lithospheric, Archean lithospheric cratons, or cratons in general, I guess, people tend to think it's pretty low. I mean, I don't know how, we have great constraints on it, but you know, if you look at the, like the Schulze's work with looking at garnet counts and eclogitic versus peridotitic. And so what's happened to the oceanic crust? And if it was the Archean oceanic crust, we expect that to be thicker because the Archean Earth was hotter, therefore the degree of melting was larger, so you'd have thicker oceanic crust going down. And so where is that eclogite gone to, in your opinion? Or is this even a problem?
Very good question. So again, I think that's going to be the value in finding more of these Archean diamonds, because it's another example of the Schulze data is based on indicator mineral chemistry in kimberlites erupted in the Mesozoic. So it's sampling the craton after almost its entire history. And there are models out there that suggest that whatever oceanic crust you may have put into the craton was somehow left. And so if you get a snapshot in the Archean, maybe before that happens, then I don't know whether we'll ever get there, but I mean, an altruistic wish is to then see, is the abundance of eclogitic inclusions versus periodic inclusions the same in these Archean diamonds that were taken out in the Archean, you know, versus what you get from the indicator mineral chemistry? So no, that is a really good question. I think the way that dynamical models are evolving, most people seem to think that eclogite is a pretty unstable feature in the lithosphere. So of course you can tweak dynamic models to suit your preferences, but that seems to be there. I'm putting words in their mouth. If Peter van McKechen was here, he'd probably wrap me over. Oh, is he? Oh gosh, oh dear. Where's Peter? Peter can answer that question.
Everywhere. I like your model of kind of a back arc setting for the Bushveld magmatism for a couple reasons. One is in the Jacobs reconstruction, you see this Western kind of subduction system that they put outside the incipient Kalahari, or the nascent Kalahari craton. So that fits that kind of larger tectonic reconstruction. You also have 2Ga eclogitic sulfide dates at Arapa and at places like Zhuaneng that are outboard on the western side of the craton. So that fits that model. And you also have a way to kind of have enough magmatism. I mean, the Bushveld's a big system, so you in an arc setting, you could replenish that wedge system with some new circulation, whereas if you have a single plume, you know, you kind of have a one-shot deal. So all those fit a nice different look for a kind of a subduction system. So I think that's good.
Yeah, thank you. I mean, I really was struck with what Laura said, though, and talking to her afterwards with analogies to the Western US about how you quickly shut off the magmatism there. I mean, how do you shut off a magmatic system that's produced 250,000 cubic kilometers of magmatism, and there's nothing else? It just doesn't go on.
Columbia River basalts are about 150,000 cubic kilometers, and they were erupted over 1 million years. So
yeah,
that's one way. But a few things. One is I have to respond to Roberta's. If you remember the histograms in our paper about mantle zenith compositions, is the distinguishing feature of cratonic peridotites is more that they don't have the fertile component. It's not so much that modern mantle doesn't have the really depleted materials. It's simply that the fertile component's missing. And this gets to the question of removing dense material. So, you know, the idea that their composition now is not what they were when they formed, right?
Yeah.
So that's one. The other one, though, I wanted to give was an example from Sloan that supports your idea that cratons are not necessarily just Archean. So Sloan is a Devonian kimberlite that erupted through 1.8 Ga terrain, and it carries 2 Ga, 1.8 Ga peridotites up. So it's a Proterozoic craton. It had the geotherm of a craton, no question about it. but it can't have that today because it's right in the middle of the laramide where, you know, tons and tons of magnetism have come through it, and the modern day heat flow is massive. So we don't have samples of it in you know, post-Devonian, but it's another way to sort of reactivate a craton, if you will. And then finally, the Bushveld looks to me like a big rift, but I don't know anything in the crust that would go with that. So.
No, but bang on with the Sloan analogy. In fact, we've just dated some diamonds from that Four Corners region, and then they're Mesoproterozoic. Yeah. Yes, it does. Yeah, yeah. I mean, I think we've got to get away from this idea that the high MgO high magnesium number olivine is a feature of the Archean. I mean, I've been partly responsible for that idea because you've got small databases in the early 1990s.
Yeah, Sloan has inclusions that have, like, Schultze had faux 93 olivines in diamond inclusions from Sloan.
And you go to New Zealand, you can find them in the prototypes in New Zealand. It's not a reliable feature.
More questions for Graham?
Hey, great talk. So this was just a tiny part of your presentation, but I got curious. How do you know the chromium from the fuchsites are from komatiites? Because I've seen these fuchsites in other places, and I know that people wonder, like, how do they form?
Yeah, we spent a lot of time on the geochemistry of those chromites. So we did laser ablation analyses of the PGE patterns along with the major element chemistry. And it turns out that the chromites from, let me get this right, the aluminium undepleted komatiites have a very characteristic PGE pattern with a ruthenium anomaly in it that is, curiously enough, not present in chromites from aluminium depleted komatiites and is really rare to see in any other type of rock. Yeah. And I don't know if you noticed the title of that paper, it sort of answered the question, where is the slave craton is very unusual. It's one of the few cratons where everywhere else you see komatiites. You go to the slave, and one of your first questions, if you're thinking, is, so where's the komatiite? And it's all in those basins.
Thank you very much. We are moving on to our next talk, and let's thank Graham again. Our next talk is by Roberta Rudnick from the University of California in Santa Barbara, and she will be talking about the evolution of the continental crust.
Is that all I'm going to see? That's what I'm going to see. Great. This is my pointer. Well, thank you very much for inviting me to here. It's I feel a little bit of an interloper because I was never a postdoc here at Carnegie, but I have had a working relationship with Rick and very much appreciate his science, and I also very much appreciate the fact that we get together in person, at least some of us, to talk about science again. It's really been exciting and fun. So, unsurprisingly, I guess, I'm going to talk about the continental crust today. And this picture just shows what the Earth might have looked like at the start with a magma ocean cooling, and somehow it transformed into what we have today, which looks very different. And if we compare the terrestrial planets, and these are shown to scale with distance from the, sorry, this is the pointer here, from the sun, we can see that not one of them is alike. They're very different. And if we think about the Earth, we can say that it has very unique features compared to the others. And the fact that we have all this liquid water at the surface, we have an oxygenated atmosphere, we have life, us, and the Earth is the only terrestrial planet that has continents. And so something special has occurred on the Earth to make these continents, and it's probably linked to the fact that we have plate tectonics. But then we can ask the question, well, why do we have plate tectonics? And that's a really big question, and I don't think we know the answer to that. Maybe it's linked to the fact that we have liquid water on the surface. When did plate tectonics start? Did it start from day one? Did it start 700 million years ago? Did it start 3 billion years ago? This is a huge debate, and I'm sure we're going to hear more about that. But one thing we can say is that it's the study of the continents that can provide insights into these important questions. And the continents provide us one of the few ways to glimpse back into deep time. And speaking of deep time, this is where I first met Rick. This was a field trip run out of the Lunar Planetary Institute Early Crustal Genesis program, 1983, so almost 40 years ago. And I guess maybe you can spot Rick. He's here sporting the cool shades and the stash. You probably can't spot me, but that's me, a pre-doctoral student about to head off to Australia to do my PhD with Ross Taylor, who's here on the right. And there's also somebody else you probably see in this photo, which is Steve Shirey, sporting his Trotsky-type look. Anyway, it was the beginning of the world opening up to me, really, and it's been a lot of fun. So back to the continents. So the continental crust has an outsized importance when we think about the whole Earth, because even though it's like 0.5 weight% of the total of the silicate Earth, very, very small component, it contains a very large fraction of incompatible elements of the Earth. And this is important because it includes heat-producing elements, potassium, thorium, and uranium. And those are the elements that produce the heat to drive mantle convection. And so if we have an idea of how much of these elements are in the total Earth, whatever's in the crust is being removed from that power source. So a couple of questions that I'd like to address today. First of all, how well do we know the composition of the crust? This is something I've spent a lot of my career working on. And has that crust composition changed over Earth history? Well, I'm not going to spend a huge amount of time on the first question. Many of you might have seen this in previous talks. Never put up a data table, we tell our undergraduate students. But the point of this is that there's been various people estimating crust composition. 1995 was a particularly popular time to do this for some reason, all the way up to 2011. And if you look across the table, there's some small variations, but not a lot. And there's very many different ways that have been used to make these estimates. And so I can conclude, I think, and we can conclude that we know the crust composition pretty well in general, and that it has this intermediate composition. It's not basaltic. Furthermore, we've known this for a long time. This is Frank Wigglesworth Clark, who the Geochemical Society Young Scientist Award, the Clark Medal, is named for. And back in 1889, he published a composition for the crust, which looks remarkably similar to what we think it might be today. So, I look at this to say, this is not depressing at all. I think this is just telling us that we've known this for a very long time. So there are things we can and cannot say about the crust. We can say that it has an intermediate composition. It's definitely not basaltic, and that's important because when we melt peridotite in the mantle, we create basalt. And so there's this mismatch between what comes out of the mantle and what the crust is composed of. It's also not, quote, andesite. I mean, as a rock type, andesite's not all that common. And in fact, the intermediate composition of the crust is mainly because it's primarily bimodal. It's granitic and it's basaltic, and you put them together and you create this intermediate composition. And as I said before, it's strongly enriched in these incompatible elements. There's things, of course, that are still debated. The composition of the lower crust is still a big question. It's pretty inaccessible, and there are different ideas about this. And how did the crust obtain this intermediate composition? There's a number of processes that have been appealed to. density foundering, also known as delamination, relamination, which is from my colleague Brad Hacker's idea that you can subduct continental crust. Well, we didn't even think that was possible until we discovered ultra-high pressure metamorphic rocks. But they tell us that crust has been subducted, and some of it's come back up. And he suggests that either subducting sediments or this subducted crust may come back up to underplate the base of the crust and, quote, relaminate it. We can perhaps melt the slab, perhaps more in the Archean than today. Even chemical weathering probably has had a role. So I want to turn, I'm not going to answer the question. I think potentially all of these processes have had a role, and I've spent a lot of my career trying to investigate, can we say one is more important than the other, and I have no conclusion at this point. But I want to spend most of the talk talking about this question as has the crust composition changed over Earth history? And maybe. Well, I would say for sure it has. It's a question of degrees. So the problem that we've heard about here is that the rock record doesn't go back to the beginning of Earth. The rock record goes back to 4 billion. There's some zircons, that go back to 4.4. And most of the record is post 3.6 or even younger. So is there a preservation bias? Is what we've seen today in the outcrops of Archean cratons what was originally there? And so that is, begs the question is how representative are these ancient rocks? And of course, one way that we can address this question is to look at sedimentary rocks, fine-grained sediments. And this has been done by Taylor and McLennan and by people before them and after them to try to get an estimate for the average upper continental crust composition. So the idea is that if crust is above sea level, it's exposed to chemical weathering and erosion, and that sediment material gets deposited, eroded off the continent, deposited, and we can go out and measure that to get an average composition of what's been exposed at the surface. The problem is that the data for fine-grained chemical sediments are interpreted in diametrically opposite ways, and I'll show you some of that. But before I go into that controversy, I want to tell you just a few slides about some of the things that we've been working on over the last, almost 10 years now, which is to take a slightly different approach from looking at shales and look at glacial deposits. And this goes back to Goldschmidt, who originally analyzed some glacial rock flour and said this is a good average of what the glaciers have scraped across the surface of the Earth. And so basically, we know we've had ice ages in the past. In fact, they go back, we have glacial deposits that date all the way back to 2.9 billion. And so we go out and sample these poorly sorted sediments. So they're called diamictites. That doesn't mean they're glacial in origin. There's certain things that tell us they're glacial, like drop stones and striated clasts. But we can go out and sample these, and we've done this around the world, and collected a lot of samples, over 100 individual samples, dating all the way back to the Archean at 2.9. And this is a picture of the Mozan group and the Pongola supergroup that was apparently definitively glacial based upon work that Grant Young did years ago. And from these hundreds of samples, we've also made 24 composites. So this is just multiple samples from the same formation put together and are making these available to the community as an upper crustal reference suite. And to date, I think the last count is there's something like 25 isotope systems that are either have been or will be measured on these samples. Comprehensive major and trace elements, including unusual chalcophile elements and PGEs, et cetera. So we've learned a lot. I've certainly learned a lot through this project. One of the cool results very early on is shown in this plot. I'm going to call it a W plot because they look like W's. So this is like a rare earth element plot, except that we've included in the rare earths, the light rare earths here, molybdenum and strontium. And strontium is a very soluble element. So if the rock is weathered, it's going to be depleted in strontium. And you can see that almost every single sample, no matter how far we go back in time, is depleted in strontium. Wyoming is an anomaly here. It's just completely flat. Molybdenum, though, is soluble, but only in its 6+ form. It's much like uranium. And it turns out we can see from these data the rise of atmospheric oxygen, which was a complete surprise to us. Here's the Archean and much of the Paleoproterozoic. Molybdenum is not depleted, strontium is depleted. But then when we pass the GOE, we see systematic molybdenum depletions. So that was pretty cool. So one of my former students, Ming Tong, got interested in this and in looking at sediments as a proxy or as a way to look back in time at crust composition. And he published this paper 2016 in Science, looking at ratios like nickel-cobalt, which these are for igneous rocks. These are igneous rocks data. So this is like a proxy for igneous differentiation, and also chromium zinc. And nickel, cobalt, chromium, zinc are relatively insoluble elements. And so we can go to sediments and measure their ratio to try to infer the composition or the MgO content of the crust that was present at the time that these sediments were deposited. And he's combined both shales and the glacial diamictites. And this is the average Archean sediment. It has a very high nickel chromium, very high chromium zinc. And if you just, well, this is not what he did, but you can just see that if you correlate that ratio to an igneous rock composition, you get a very high MgO concentration for average crust that was exposed in the Archean. And then you get to the young post-Archean sediments, and they're much more like what we expect the upper crust to be today. So we published this paper and suggested that maybe there was this fundamental change in upper crust composition, what was being eroded, and that maybe that correlated with the onset of plate tectonics, with the simple idea that you need water, subducted water to lower melting temperature to drive the formation of granites. And so we started making much more abundant granites post 3 billion years ago. Okay, so that was one story. And then later, Nicolas Defal and his group at Chicago re-evaluated the question of looking at trace elements in sediments. And this is a paper they published in 2000 and 2020 EPSL. They took a large database and they figured out what are the most useful elemental ratios to use. And this is what they came up with for the proportion of komatiite, mafic, and felsic rocks as a function of depositional age. And you can see that, yes, so we agree in the fact that the crust composition has changed because they also have a greater proportion of mafic crust that decreases with time. And we all know that komatiites have decreased over time. But they come up with a bulk silica ratio that really doesn't change very much through time. And this is very different from what we inferred on the basis of the nickel cobalt. And one could argue, well, maybe your nickel cobalt ratio is just being influenced by the komatiite component, and that's all you're seeing is the disappearance of komatiite. But you can find elements that are sensitive to mafic rocks, not komatiites. And one of those elements is copper. And this is work done by Kang Chen, who was a visitor to our lab for about a year. And what this shows is igneous rock averages as a function of MgO content versus copper concentrations. So we get a mantle-derived melt out here somewhere with high MgO, and copper is incompatible initially during differentiation until the melt becomes sulfide saturated. And then the copper concentration drops off quite dramatically. And we see that both with SiO2 or MgO. And only basalts have very high copper concentrations. So copper is uniquely sensitive to basalts. And then Kang measured the glacial diamictites, every single one of them actually, not just the composites, for their copper concentrations. And he did this by isotope dilution, so it's really nice data. And what you can see is that there's a clear trend of copper versus age, and these are the means and the averages and the medians for each age population, going from 3.2 to 0. So there's this dramatic drop-off in copper concentrations with time. And that would tend to support a much more mafic, a lot of basalt, or maybe pickrite in the Archean. And so these are the ratios you get when you use the copper concentrations. For a 3 billion-year-old upper continental crust, according to copper, it should be dominated by basalt, not tonalite or whatever, TTG. And felsic rocks can be present, of course, but they were subordinate. Anyway, that's where it stands. We don't have an answer. We get sort of like, the blind man and the elephant, looking at different parts and getting different answers, but this is where it stands. Now, all of us were asked to talk about future directions. And what I would like to focus on here is that Carnegie, and in particular Rick, have done a tremendous job of mentoring the next generation of scientists. And in my opinion, this is the most important future direction. That is, this has to continue. And I would also like to suggest that, I'll call it the Rick and Steve model. The Rick and Steve model, which has really made Carnegie stand out on the map, is that they build state-of-the-art facilities, then they hire excellent technical staff, 2 of them or more maybe sitting here in the audience, Mary and Tim, who I know. Then they use this to tackle really important scientific questions, but they have operated with an open door policy the whole time that I have been aware of Carnegie. This is huge, and this is so different from a lot of the models out there. Oh, this is my lab, these are my data, and I'm not going to share them with anybody and let you into my lab. So, this is why there's been such tremendous output and discovery coming out of Carnegie. And all I can say is thank you, for being who you are and operating in this mode. And I'd like to say that I hope that Carnegie would continue to lead the world in Cosmo and in geochemistry and with this open door collaborative science. And I know Eric's not here. I don't think he's listening, but if he ever hears this, you definitely got to start hiring like yesterday and more than one position in order to sustain this type of scientific discovery and mentoring and output. So I'll get off my soapbox and say science and life can and should be fun, and Rick knows showing us the way. So thank you very much. I really appreciate being here. I really appreciate all the science we've heard. And I'll take some questions if you have them.
Thanks, Roberta. I haven't thought about this a whole lot, but aren't there detrital pyrites in the Archean, and couldn't that affect copper?
Well, pyrite doesn't have much copper.
Or
Chalcopyrite
sulfides?
might do.
Sulfides.
So let me think about this. There are detrital sulfides, and once you get past the GOE, they pretty much disappear. And has that influenced the copper, or to what degree has that influenced the copper? I don't know the answer to that. I think the answer is probably not much, because most of the sulfides that are forming in the Archean are going to be nickel-rich sulfides or iron sulfides, and probably not a lot of chalcopyrite. We certainly have done, we actually did a study of the detrital sulfides in these deposits. And chalcopyrite's present, but it's certainly not dominating the sulfides. So I suspect, without having done much investigation, just thinking here on my feet, that probably the sulfides are not dominating the copper in the Archean sediments. But it's a good question, and we can certainly look at that because we do have the data.
More questions for Roberta?
So the MgO content of your earlier samples are very high. I mean, they're way up there,
Yeah.
higher than average Cumati. Can you comment on that? And I mean,
So
I guess what struck me is do you think there's any effect that the diamictite sort of environment has on say magnesium? It just seems very high.
well, first of all, let me be clear that this MgO content is an inferred MgO content, because you can't measure sediment and hope to get MgO because it's so soluble. So this is the problem with trying to reconstruct major element compositions, looking at shales or diamictites or whatever, which is that the diamictites, I should also mention, I guess you kind of saw that, they all have this weathering signature. And we spent a lot of time trying to figure out where that weathering signature came from. We think it came from the regolith that the glaciers were scraping off, that it's almost certainly not post-depositional. Most of these are submarine deposits, and we don't think it's synglacial, so we think probably it's a weathering signature that came from scraping across the surface of the Earth. So MgO content's going to be really low because MgO is soluble. So these are inferred on the basis of these ratios of nickel, cobalt, and chromium, zinc. And in fact, when Ming came to me with this, and he showed me this, I said, that's ridiculous. There's no way there can be, on average, 15% MgO in the Archean upper continental crust. I think 15 is too high, but I still think it was very high. It might have been 10. It's still high. And I think, I mean, it seems to me there's a very strong case to be made for a much more mafic exposed crust. Now, whether you call that continental, I don't know, but it's above sea level. So it's really not crust like we know it today, but it had a lot more basaltic component in it.
Yeah, thanks, Roberta. This is really interesting. Kind of touching on that last comment you made, you know, the sort of textbook view of Archean cratons is you have these basaltic 2.7, 2.8 Ga packages erupted onto and sometimes through TTG crust. Like, is there any, I guess, can you sort of, I don't know, speak to that of maybe, is this reflecting erosion of this basaltic, you know, top layer or something like that?
Right, so could the crust have been stratified with a basaltic cap and then and a granitic middle crust? Possible, you know. All we can say is what was sitting at the surface and getting scraped off by the glaciers or eroded in the cases of, you know, the fine-grained sediments. So that is possible.
Thank you, Roberta. Oh, another question. Okay. Rick, I guess.
Yeah, Robert, I just want to say I vehemently agree with your last slide.
That life can be fun?
Yeah. Well, the next to last slide. A question for you, though, just hypothetical. So can you explain the difference in magnesium concentration between Archean and post-Archean if you simply assume that the crust is bimodal, which is not true, but close to it.
Well, in the Archean, it was pretty bimodal.
Yeah, but then the point is, can you just explain that difference by the higher magnesium concentration in general, not only of commoditeites, of course, but also of Archean basalts compared to modern basalts? Or do you really have to adjust the ratio of basalt to granite in those?
You know, according to these data, I mean, this copper should be pretty sensitive. These are Archean igneous rocks, right? So copper should be a pretty sensitive tracer for those. And according to that, which 10 weight % is the maximum copper, this is what we get. So, and so those are error bars. So you could get as low, the lowest we could go is like 58% basalt, and then most of the rest being felsic.
But where would you go today to find a piece of crust that has 75% basalt in it?
I'm sorry?
I mean, mass proportion of basalt or felsic crust. So,
so
I don't know a section of what I would call continental crust that has 75% basalt in it.
Well, exactly.
Yeah.
Exactly.
Yeah.
So the question is, did the crust that was above sea level in the Archean look like the crust today?
Yeah.
And I would say the answer, according to these data, is probably no. It probably looked very different from today. Yeah.
Very quick.
Yeah. Did you guys look at the clasts in these diamictites, you know, to see if there's any change between tonalitic to more granitic compositions with time?
We do. We haven't done a systematic study of the clasts. This is something sort of we've got to do this, right? And I would say that, you know, from what I've seen, we see, well, first of all, the other thing I want to say, I'll just back up for a second. I have this debate with my colleague Francis McDonald all the time. He says, oh, you know, the Neoproterozoic ones, you're just looking at local provenances and whatnot. And we see that for sure. We see these are not homogeneous. We can see A-type granites in the sources. We can see banded iron formations in some of the sources. And typically, those regional signatures correlate with clasts that we see. So we do see, you know, pieces of banded iron formation or quartzite. Mostly we see things like quartzites and a few granitic rocks. But we haven't done that study. But even with those local provenance, even though that we're seeing the really strong effect of local provenance, what's amazing to me is that we still see these systematic changes over time. Very, very systematic. And so I think that is telling us that we are seeing how the crust has evolved over time, looking at these types of rocks.
Thank you again, Roberta, for the nice talk. And
oh, shit. I've done it again.
We'll be moving on to the talk by Marion Garçon from CNRS Clermont-Ferrand. And the title is Episodic Growth of Felsic Continents.
Is it okay? Where is that? Here? Is it okay? Yeah, it's good. You hear me? It's fine? Yep? Okay, great. Okay, maybe I'll put that here. Okay, so I'm pretty much going to be talking exactly the same thing as Roberta said, but you'll get the other point of view, which is great so that we can have discussion afterwards. So today I wanted to talk about felsic continents. Do we have them? Okay, that's going to be better. Thank you. Okay, so I wanted to talk about felsic continents again. But what does that mean exactly? Do we have them everywhere and today and also throughout Earth's history? So I was a bit frustrating this morning because we didn't hear a lot of neodymium. So don't worry, Rick. I'm going to pronounce that word about 20 times probably during the talk. But I'm not going to be talking about isotopes, sorry. We're going to stay on the parent-daughter element ratio. Okay, so we all know that there are two different types of crust on Earth, and the easiest one to understand, at least at the first order, is the oceanic crust. So it has been estimated that its average silica content is about 51 weight %, which make this crust mafic, and you would expect it to be made of gabbro and basalts, and indeed, this is pretty much the case, at least at the first order. Now it becomes much more complicated when you're talking about upper continental crust. So I would use either the word continents or upper continental crust, but I will mainly focus here on the upper part. We can talk about the bulk continents if you want at the end, but here I'm going to be really looking at the first 10 kilometers. So the best estimate that we have for these first 10 kilometers has been suggested by Roberta, Rudnick, and Gao in the Treatise of Geochemistry, and it's about 67 weight %, which make the crust felsic, but it is not fully covered by granites, as we've been discussing, and it's in fact very heterogeneous in terms of lithology. So the way this estimate has been done is mostly based on surface averages. So people have collected samples on the field, they have measured the chemical composition, and then they have made a big average, and then here you go, you have this value here. But in fact, it's a bit more complicated, because if you're looking at the distribution of igneous rocks on continents, so you have here the distribution as a function of silica content, you can see that the distribution is indeed bimodal. It's not like a single Gaussian curve. And you have two peaks at about 50 weight % and another one
at 73 or 72 weight percent. And the average upper continental crust is almost in the middle. If you're looking at the bulk continental crust, which is at about 61 weight percent, it's right in the hole, which is some of a problem. If you're looking at the volcanic distribution, distribution of volcanic rocks and that of plutonic rocks, again, you're not on a peak. So what this means is that the average silica content of the continents, in fact, reflect a mixtures between mafic and felsic volcanic and plutonic rocks, if you're looking at the igneous part only. But it's getting even more complicated when you're actually looking at global lithological maps of the continents. So this is today. You can see that the colors that dominate here are yellow and orange, which are in fact sediments. And if we're looking at this quantitatively, water and ice plus all the sedimentary units, in fact, represent about 3/4 of the continental surface. So metamorphic rocks here in green and felsic and mafic lithologies that are represented in red and purples in this map do only represent 26% of the continental surface, which is not a lot. So if we remove all these sediments and try to quantify how much mafic and felsic rocks you actually have on the continents, and you assume that metamorphic rocks are felsic, so we don't know anything about these rocks if they are really felsic here, but this is something that we can expect. Then we have felsic modern continents. So we have about 3/4 in terms of proportion of felsic and metamorphic rocks, and then the rest in terms of mafic and intermediate lithology. And this is true almost everywhere on Earth. Now, if you, so we're pretty happy, modern continents are felsic everywhere, which is fine. But if you remove the metamorphic rocks and looking only at the igneous record, here you're looking only at 13% of the continental surface, and you end up with a crust that is half-half mafic and felsic. And in some places, you even have more mafic and intermediate lithologies than felsic one. So it means that in that case, modern continents are not that felsic anymore. So it means that if you had to estimate the composition of continents based on continental surface exposure only, the answer is not that clear, and it is mainly because it is blurred by sediments and metamorphic rocks. Hopefully, we have another solution, which is looking at the sediments, the terrigenous sediments that are the erosion, that contain the erosion products of continents. And if we find a good proxy to do that, then you can maybe say something about the modern composition of continents, but also the ancient composition. So here I'm going to be talking about samarium and neodymium. This is one of the proxy. Roberta talked about copper, but we can also use rarest element ratio. So what do you need to have a good tracer? First, it needs to be a tracer that well discriminates felsic from mafic sources. So this one is quite good. You can see that we have a good correlation between the samarium-neodymium ratio of felsic and the mafic rocks. And the second condition is that this ratio is not significantly affected by sedimentary processes. So samarium and neodymium are quite immobile, so it's pretty fine when we're looking at this proxy in ancient sedimentary rocks. And here I'm showing a plot of the samarium-neodymium ratio in fine and coarse-grained sedimentary rocks as a function of their deposition age. And you can see that the two curves are quite similar. So it means that this ratio is not fractionated during the transport of sediments by mineral sorting. And so basically, when we're going to measure samarium-neodymium ratio in the sediments, we could assume that it represents that of the sources. So we've been doing a big compilation of data, of published data on sedimentary rocks. So you have here all the sedimentary rocks that we have found and that have been measured for very precise samarium-neodymium ratio as a function of time. We have just been here all the data every 200 million years. So this is the pink curve that you see here. And using the relationship that we show in igneous rocks, we have converted this samarium-neodymium ratio into average silica content for the eroded continents through time. And we end up with this yellow curve here with a 95 confidence interval that is pretty much similar to the modern upper continental crust up until 3.5, 3.7 billion years old. So this is very different from what the team of Roberta get with the copper concentration. And indeed, there is very contrasting results in the literature. So you have you have seen already some of these pictures. But basically, we have a bunch of new studies, I would say, in the past 5 years, showing that the crust might have been felsic in the Archean. So you have this study here based on major element composition of sediments. Then a bunch of study, including mine, based on trace element ratio in sediments. And this maybe more contested study about titanium isotopes in sediments. And as I said, or you just saw in Roberta's talk, there are also studies that are showing that the crust in the Archean might have been mafic. Also in this data, you can see that we have pretty unresolved composition here, and it's quite spiky. So we were wondering whether we were not, in fact, seeing some local effect or local catchment area that had mafic composition. So we've been looking into 2 case studies so far to assess whether we could have local effect. In the next few slides, I'm going to showing you results just for the South African craton and then the Australia, because we have rocks that cover a wide range of ages. And we've been combining 2 different approaches to see whether they're telling us the same thing or not. So we've been estimated the average silica content of continents based on the samarium-neodymium ratio, and also looking at surface exposure as a function of age, just to see whether they match together. So let me back up a little bit. So if we're looking at the silica estimate based only on samarium-neodymium ratio for the South African sediments, you can see that this is pretty much the same as the global scale, meaning that you have a composition that is very felsic and that match the upper continental crust composition, even in the Archean. And this is quite similar to what we see in terms of rock lithology. So here it's a bit complicated figure, but you have basically each color that represents a lithology. So the felsic ones are at the bottom, TTG, granite, felsic volcanic rocks. Then you have the mafic unit here in purple and the sediments on the top. And so these are cumulative proportion as a function of age. And the idea was just to see what type of crust the sediments could have seen through time, and whether this globally match with what we have here. And in fact, when you're looking, for example, at 3 billion years old, you can see that you have this huge amount of felsic units, if you assume, again, that metamorphic rocks are felsic, and that mafic lithology, included cometites here, really represent a very small proportion of the crust. So, of course, this can be biased by erosion and tectonics. We all agree with that. But it is still interesting to see that it matched pretty well with the estimate that we get from silica content. The other interesting thing is how the sediments are becoming super important very lately in the history of South Africa. And looking at Australia now, it's exactly the same story. The silica content of based on samarium-neodymium ratio of sediments is quite felsic and similar to modern upper continental crust. And here at 3 billion years, we again have a lot of felsic lithology. So we have here an interesting higher proportion of mafic volcanics. But we do think that this is linked to the way we're doing this, because It's very difficult to match the geological maps with the ages of the different lithology, and most of the time we have range of ages. So here what is representing here is the minimum age. So you might have a gap between the minimum age of the TTG or all the granitoids and the greenstone belt actually, but we have to look in more details about that. Okay, so to conclude about this, what we can say that the modern continents are felsic, we're all happy about that, but they're not fully covered by granite. And this is really important to keep in mind that the average silica content of the continent, in fact, reflect a mixture between volcanic, mafic volcanic, and felsic, probably plutonic and metamorphic rocks. And most of the proxy now are showing that the ancient continent might be felsic. And I think just showing Roberta's talk and looking at this data again, that maybe the problem might be in the conversion of the silica contents towards proportion of basalts versus granite, because this is what it looks like today. But if here the peaks are not exactly at the same place, when you want to convert the average silica content or the average magnesium content of the crust into a proportion of basalt versus felsic units, then you might be shifting the proportion towards one way or the other. And to finish, the most important probably, I would like to thank you, Rick, for taking the time to show me everything in the lab, because I didn't know anything when I came here as a postdoc about thermal ionization mass spectrometry, and you taught me everything. And also thank you for all the interesting discussion we have about every Earth processes. It was really great to be here, and have a good retirement.
Thank you very much. Any questions?
So Marion, I was a little bit unclear on how you developed these lithology profiles. Is that based on map?
Yeah, so it's
map
not my
outcrop
work.
Or?
So this is Jean-François Moyen,
Yeah.
who is in Clermont-Ferrand. And so, yeah, it's a bit complicated because you have to match the geological map.
Yeah.
So you need to have relatively precise geological map with good information about the lithology.
Yeah.
And then you have to combine that with the age of the different lithologies, so which is often not in the same database.
Yeah.
So this is why he's been producing these only these two maps so far. So South Africa, he knows the stuff pretty well. So he can assign an age and a composition and differentiate what is a TTG from a granite, for example.
Yeah.
But the database is not that clear in Australia, where you cannot say, well, you can, but you have to dig into the data to see whether this is granite or TTG, for example.
Type of granite, yeah. Yeah.
Mm-hmm.
This is going to be an ignorant question, but I don't understand how you generate your correlation between your samarium-neodymium ratio and the silica content. And the reason I ask this is that I worry about the fact that basaltic rocks have significantly lower rare earth element abundances than felsic rocks. And so just using the ratio, it seems like there could be a bias. So I'm just curious how you correct for that.
Yeah, so I often have this question. Roberta can ask me that, and also Ken Condi, and so I can go to this one. Basically, this is exactly, well, what I'm doing here implicitly account for the concentration, because this is just an empirical way to see the relationship between silica and samarium neodymium in igneous rocks. So the curvature here that you have is in fact linked to the fact that there is much less rare earth elements in mafic rocks than in felsic rocks. And so just to convince you, you can do a mixing between an igneous end member here and a felsic end member here and a mafic end member here. And this is the curvature that you get when you take into account the difference in concentration in terms of neodymium between the two end member. And so it fits pretty well the empirical way, which is just averaging every one weight percent. And you end up, in fact, when you're taking these end member, and this is maybe the problem, that we should take an end member here, and here who knows where it is. But if you take these one, then you end up with having a modern upper continental crust that is made of 20% of mafic lithology and 80% of felsic one.
Yeah, I understand, and the mixing line is really convincing, but the mafic end member, you know, that's pretty light rare earth element enriched on the end there. I mean, a typical basalt should be like 0.22 or something like that.
Well, so it depends which basalt you're taking. And of course you have, let's go to another one then. You have different trends depending on what you're taking, if you include Moabs in it, and if you do not include Moabs in this mafic end member unit. And you can so play with the different tectonic settings and with the different ages of the trends. And you can see here that indeed you have different trends depending on whether you're using Archean or post-Archean rocks. But so either you taking, so what I did in the previous slide is just take an average of everything and make the conversion. But you can try to play with these two different trends. The problem is that you don't know when does that happen. Why should we take an Archean and a post-Archean data set? Here you're making a strong assumption that something happened at 2.5. So I don't like this. You can also make a smooth transition like in the Greber paper. They're making a smooth transition with their relationship between titanium and silica and the other trace element ratio they're using. So they're transitioning from something from 3.5 to 1.5 in terms of this relationship. And so, but the point is that whether you use Archean, the Archean trend or the post-Archean trend, you end up with having something that is felsic. By felsic, I mean above 60 weight percent on average. But it's true, this is highly dependent on which rocks you're going to take as an M member.
If there are no more questions, then we move on to our last talk. Let's thank our speaker again. And the last talk will be by Robert Stern from the University of Texas at Dallas. And his title is Biogeodynamics, Linking Tectonics and Biologic Evolution.
Well, thank you. I'm very happy to have this position as the last speaker. Yeah. Could you help me? Thanks. All right. So lunch waits. Let's see if we can work this. Nope. Nope. There we go. So, you know, my 2 years here at Carnegie were wonderful. We got to enjoy the delights of the city, and we added a beautiful young daughter to our family. So now I was here. This was ostensibly a farewell party for me, but in fact it was a welcome party for Rick. And here you can see a number of people. David James is christening my departure. I think Fuad is helping a little bit with the effects. Rick's back in the back. Koichi Ishizaka, Mark Harrison, Emi Ito. I forget his name again, Rick, you said on the far right? No, that's Koichi Ishizaka. That's his hood. Yeah. And then a very strange robot, nothing like the Roombas of today. So this was really the beginning of the Carlson era. So I want to show you mostly about the future. And we in geosciences have been laboring under the idea of uniformitarianism, which in some ways has inhibited our ability to think about early Earth history. So now maybe I can get some help from technical to get this video on. It's only a 2.5-minute video, but I want to show you this for two reasons. One is the idea of emergence is a really powerful idea that transcends our field, and it basically applies to everything. And the other is videos are an extremely powerful way to communicate to a very large audience that has different strengths and weaknesses. Did you find it? No, I have to go back and click it. Yeah. Could you guys bring this up? All right. No, you got to copy and paste. I got another one after this. Yeah, you have to get out of it. Okay, thanks. What's that? They're going to handle it in there. Yes, that's great. It's going to make my life a lot easier. Just copy and paste and open. But I haven't quite mastered the embedding of the videos. Yeah, someday. We need some younger people. There we go. And we need sound. This is why closed captioning is so important. Hey, can you guys turn the sound on? Oh, well. You have to do something here.
In this short groundwork article, they discuss how thinking about emergence can help us understand Earth and other silicate planets and moons and how their tectonics evolved. Convecting silicate planets are high-energy, far from equilibrium systems, and as their interiors cool, their lithospheres respond by becoming The concept of emergent phenomenon explains that any high-energy, far from equilibrium system will organize itself in ways that cannot be predicted from knowing its individual components. In a nutshell, an emergent system will organize itself so that energy flows in the system is not a theory. It is a way of looking at many different kinds of energetic systems. Emergence is closely related to self-organization, complexity, and evolution. Many things exhibit emergent behavior. Animals, ecosystems, system complexity. Entirely new properties and behaviors emerge, without direction and with characteristics that cannot be predicted from knowledge of the constituents alone. In the January issue of GSA Today, Bob Stern of UT Dallas and Taras Guria of ETH Zurich discuss how thinking about emergence can help us gain new perspectives about Earth history. In this short groundwork article, they discuss how thinking about emergence can help us understand Earth and other silicate planets and moons and how their tectonics evolved. Convecting silicate planets are high-energy, far from equilibrium systems, and as their interiors cool, their lithospheres respond by becoming thicker, denser, and stronger. On Earth, these tectonic styles are likely to have merged into the plate tectonic system we see today.
Okay, now let's see if I can get back in. Can I get back into
Want to learn more? Check out Earth evolution, emergence, and uniformitarianism in the link provided below.
Can I get back into the? Okay, good. All right. So this is something that we've started it's called, at UTD called Geoscience Studios. It's all students. My main role is to help them refine. Stand by. I think I will go on mute. Oh, good. I can do that. Did I do something? Click to exit full screen. Okay, now we're back to it. So involving students in this is a wonderful creative activity. So for undergraduate students, the thing that they do is choose a topic they want to learn about, because even to put together a 3-minute video requires, you know, a lot of work. It takes a semester for them to do it as part of a course I teach each spring. For graduate students, they're working on higher level projects aimed at upper division undergraduates that also involve a significant component of assessment. What works in the classroom, what doesn't? And this is an opportunity to reach out to a much larger population. Carnegie should think about doing something like this. Obviously, the student model wouldn't work, but you guys have got staff and you've got so many interesting stories to tell. And what you find is, okay, you can't tell any of the stories that we've heard today in 3 minutes, but you can take the nutshell of that, or you can take the nut of that and give enough to interest a young person to go into the literature and learn more. They don't like to read just to read, but they do like to read if they're interested in something. So I really hope that Carnegie will set up some kind of a Carnegie Science Studios. Now Carnegie is not without a video presence. Let's see. Oh, I got to do it here. Yeah, too much technology for me. So Carnegie Science videos, they are your wonderful neighborhood science videos, presentations, but they're long. They're an hour long. And if you want to know about your average person's attention span, listen to radio and time the music. So we'll listen to a song that we like for 3 minutes. Very few songs get played multiple times because, you know, after a while you get tired of it. But, you know, maybe in the old days they would listen to an hour-long piece, you know, a concert or something. But 3 minutes is the optimum time. And 5 minutes, okay, maybe they'll hang on for something like Queen's Bohemian Rhapsody. But, you know, it's got to be special to go longer. So Carnegie, with all of your stories and all of your groups, it'd be wonderful if you guys started finding a way to tell 3-minute, 5-minute stories aimed at the larger audience, you know, people that are not going to ever come to this kind of a conference. And I think the directors are going to have to take the lead in that, because they're going to have to pigeonhole scientists who have really good stories and work with the staff who are going to make the videos to talk with those scientists and turn their excellent science into a 3-minute thing that will stand up and be popular. Let's see. Oh, yeah, this one. All right, so this is just what I'm going to finish up with here. Can we try this one? I think we've perfected the problem. So this is a video. This is, I'm making my talks now, AGU and GSA talks, as videos and then posting them. AGU has gone to this, sort of 5-minute talk thing, which is a little bit annoying because we like to talk longer. But the reality is, if you know you've got 5 minutes and you can make a video, give yourself enough time, that's 600 words, and then, all of your stuff can be read. You can go to the literature. Somebody wants to follow up, they can go to the literature. There was about 25 people in the room at New Orleans, and since we made this, posted it on YouTube, over 1,600 people have seen it. So if you want your science to be noticed, make a video about it, and present it, of course, at the meeting, and then post it on YouTube. Let's hopefully this. Okay, and you can see that there are some technical issues that remain between the traditional lantern slide presentations and this new future, but I don't think there's any question that the future is going to have more videos. I mean, we don't know what the future holds. Some of us are afraid of it. Most of us probably are. But the reality is, there's going to be a lot more videos, and the incredible stories that I heard today and yesterday, they're begging to be told to the greater public. I think we're almost there, except sound in the beginning. So obviously, I've got a slightly different opinion than many people in this room about when plate tectonics began, but I'm no danger of convincing any of you in my position. But the reality is, if it explains some things, then maybe you'll be a little more sympathetic to it. And life is the big thing to explain, especially because you've got this incredible effort in life in Carnegie that is pretty isolated from the solid earth stuff. But in the future, I think we're going to see those two groups working more closely together. And what I found with in the margins and PRISM's program was, one of the great things about that was the geophysicists talk to the geochemists. And if you do that, you have to cut down your neodymium isotopes a little bit in the hopes that they will
other actively convecting solar system silicate bodies to conclude that some kind of single lid tectonics dominates, that plate tectonics is unusual in space and time, and that conditions of lithospheric density and strength favoring plate tectonics only happened late in Earth history. These insights motivate reinterpretation of the last 1.6 billion years of Earth history, the Mesoproterozoic, Neoproterozoic, and Phanerozoic eons. We demonstrate how geological indicators of plate tectonics are missing in rocks older than about 800 million years, then show how Mesoproterozoic rocks. Hi, I'm Bob Stern, and we'd like to tell you how complex life and plate tectonics evolved together. How life started on Earth may be the biggest mystery, but right behind this is the question of why it took 3 billion years more before complex metazoans evolved. It appears that this mega lag time happened because the modern plate tectonic regime took that long to evolve. Our presentation explains how we reached this startling conclusion. We explain our emerging understanding of how and when plate tectonics started in Neoproterozoic time and explore how this spurred the explosive evolution of complex life. We combine our understanding of how the sinking of dense oceanic lithosphere in subduction zones with examples from 3 other actively convecting solar system silicate bodies to conclude that some kind of single lid tectonics dominates, that plate tectonics is unusual in space and time, and that conditions of lithospheric density and strength favoring plate tectonics only happened late in Earth history. These insights motivate reinterpretation of the last 1.6 billion years of Earth history, the Mesoproterozoic, Neoproterozoic, and Phanerozoic eons. We demonstrate how geological indicators of plate tectonics are missing in rocks older than about 800 million years, then show how Mesoproterozoic rocks differ in a way that is best explained if they formed in a single-lid tectonic regime. The Mesoproterozoic single-lid episode slowly transitioned into a global plate tectonic mosaic during the Neoproterozoic, the same time period when large complex life emerged in the oceans. It is axiomatic that such a profound tectonic transformation disrupted Earth's climate, providing the fundamental cause of the prolonged late Neoproterozoic climate crisis known as Snowball Earth. Finally, we explore how the Neoproterozoic tectonic revolution stimulated biological evolution. Three main effects are identified. First, enhanced uplift, erosion, and weathering accompanying continental collision and widespread ash from explosive arc volcanism increased the supply of nutrients such as phosphorus and iron to the oceans. The increased nutrient supply stimulated all life, including phytoplankton. Greater phytoplankton activity increased the concentration of free oxygen in the hydrosphere, making the evolution of large marine creatures possible. Second, plate tectonics ameliorated climate by drawing down atmospheric carbon dioxide as a result of increased weathering and photosynthetic activity, and provided new places to store carbon in passive continental margins and subduction zones. A moderate climate is essential for metazoan vitality. Bacteria can survive at temperatures greater than 100 degrees centigrade, but complex life thrives in a smaller temperature range, 10 to 30 degrees centigrade. Third, the formation of isolated habitats is critical for speciation and evolution. Single-lid tectonics does not create marine habitats easily, especially new continental shelf habitats where Neoproterozoic and early Paleozoic evolution was concentrated. In contrast, plate tectonics creates new continental shelves and diverse marine habitats frequently. We conclude that the enhanced nutrient supply, climate, and habit formation accompanying the Neoproterozoic tectonic revolution caused the biological revolution. We hope you are as excited as we are about the increasingly compelling case that complex life and plate tectonics evolved together in Neoproterozoic time. Understanding the coevolution of life and tectonics on Earth is the focus of biogeodynamics, an emerging field at the interface between geodynamics, geomorphology, climate, ocean and atmospheric sciences, geobiology, ecology, and biology, with special focus on how changes in these systems are interrelated. Please visit the biogeodynamics website at ETH and check out the several student numerical modeling projects. Just Google ETH Biogeodynamics. Also check out Tim Gray and others' Thursday poster, PP 45A 1086,
that's the
Global Scale Numerical Modeling of the Emergence of Plate Tectonics and Complex Life on Earth.
Okay, I think that's it. Thank you. So that's the talk. Rick, enjoy your retirement, and you know,
Airlines is a complete...
That happens too. And thanks to the guys back there.
Yeah, apologies for the technical difficulties. I'm sure everyone is starving right now, but maybe a couple quick questions, if there are any.
Stunned silence.
Thanks, Bob. Regarding the change from, a hotter or warmer climate to a cooler climate with the onset of plate tectonics, there was this fairly large glacial episode in the Paleoproterozoic, which is probably on scale with Snowball Earth. So how does that fit into that scenario?
Well, that's related to the CO2 drawdown due to photosynthetic activity, right? It's not, it happens during a magmatic low. you know, the 2.3 or so, 2.4. I mean, that's an interesting episode. One of the things that happened with my investigations into when plate tectonics started is that it was too simple of a question. The real question is, what has Earth's tectonic evolution been? And emergence is a really useful way to look at that. It's not an on-off switch. It is, things happen. So I don't deign to even talk about, I mean, I'm working on the Paleoproterozoic now. It's clearly got evidence of something like plate tectonics. You know, there's ophiolites, there's paleomagnetic evidence of motion. It's very different than the Mesoproterozoic. And before that, you have this lull that Kent Condy and others have looked at about 2.3 when the GOE happened. The Archean is way before that. I may be dead before I get a chance to look at the Archean, but that is a particularly interesting thing. So the idea that plate tectonics started at this time, or this time, or this time, it may have started multiple times, but the episode we're in now has been remarkably long. Because to get something like a Carnegie requires about 1 billion years of evolution. I mean, the first complex non-sponges happened on the order of 800 million years ago. And you know, one of the challenges, why don't we get any evidence of intelligent life anywhere else in the galaxy? Well, it should be there, except if plate tectonics is something that's unusual and maybe doesn't last very long, then you don't have time, even if you have a primitive life on a planet, for the complex life to get to the point that we are. So that sort of answers your question and maybe a little bit extra.
So you've thought about this a lot. What are your thoughts on increasing complexity in relation to the geological processes that produce the niches and habitats? Is there any direct correlation between the emergence of plate tectonics and less diversity early on?
Yes. Yeah, it's, so the Paleoproterozoic thing that kind of looks like plate tectonics only lasted 200 to 300 million years. So that's not long enough to really get us. And life was much more primitive. So eukaryotes have to evolve first. There were no eukaryotes at 2.3 billion years. So, you know, the complexity of single-celled organisms had to get to a certain point. The oxygen had to get to a certain point, because if you have large animals, they require much more oxygen than single-celled organisms. And so plate tectonics came at a very good time for life, because it basically did these three things, you know, enhanced nutrient supply, ameliorated climate, once we went through this nightmare of snowball Earth. And the third thing was, because you have this rifting and collision and continents moving around, you've got all of these different niches. And in the late Neoproterozoic and the beginning of the Paleozoic, the critical environment is shallow marine shells. And so we break up a continent, you've just made a hell of a lot of habitats for things to occupy, speciate, and start eating each other.
You've got a lot of new surface in the photic zone and all that kind of stuff.
Yeah, and right there ready to be occupied if whatever comes in.
If there are no more questions, then let's thank our speaker again.
Thank you.
And I'll pass on the microphone to Mike.
Thank you. And I know everyone's very hungry, so I won't keep you long. I just have some thank yous to give. First of all, excuse me, I'd like to thank all of our speakers. What an awesome day and a half of science. That was truly remarkable. And from top to bottom, those were such excellent talks. And they really did manage somehow to cover the impressive scope, breadth, and depth of all the science that Rick's been involved with and inspired over the past 4 decades and more. So we really appreciate your taking your time and delivering those fantastic talks. So a round of applause for our speakers, both online and in person. And then I'd like to just thank everybody for attending, again, both online and in person. I think Michael told me that we've had around 60 folks online throughout the past day and a half, which is quite impressive. And I just wanted to also say to Roberta, yes, we will maintain that openness in our science. And I hope to see you all again here on campus. Go to our website and migrate to the Global Visitor Program page. And if you want to come spend some time with us, please do that. And also, your remarks were recorded, so that's a good thing. And I really do also want to thank all the people that made this possible. So Michelle and Anna and Katie and Natasha and Gary and Maceo and all the facilities guys, and Daniel and Gabor and Michael have been sitting in that little room for a day and a half. So really a round of applause for everyone who made this happen. And of course, finally, thanks again to Rick for everything that you've done at Carnegie for again, 42 years and more. And like I've told you before, and you'll appreciate this, being from California and being of the right vintage, of course you can check out, but you can never leave. And we expect to see you here for a long time to come. One final thing, we have boxed lunches for everyone. But before we're going to pass those boxed lunches out, we're going to make you line up and have a group photo so that 20 or 30 or 40 years from now, we can have one of those old grainy pictures to look at. Okay, so we're released on the patio, so we can go there right now. Thank you.